Hello, dear listener or reader. Welcome. Welcome to this quiet space, a gentle corner carved out just for you. Away from the hurried whispers and insistent demands of the world outside. Here, there's no need to rush, no need to understand everything at once. This isn't a lesson, nor is it a prescription for any ailment of the mind or body. Think of it, instead, as a soft invitation, an invitation to let your thoughts drift, like autumn leaves on a slow river, carried by a gentle current of curiosity. Where are you right now? What time is it for you? Perhaps the sun has dipped below the horizon, painting the sky with hues of twilight? Perhaps the moon, a silent silver coin, is already high in the velvet expanse? Or maybe it's still the quiet embrace of dawn, the world just beginning to stir. No matter when or where, know that in this moment, you are exactly where you need to be. There's no pressure here, only a soft hum of wonder, a gentle whisper of the universe's greatest stories. We're simply going to explore some vast ideas, to let our minds wander through concepts that are almost too grand for human comprehension, yet utterly fascinating. It's a journey not of destination, but of gentle meandering, a way to soothe the busy mind, to perhaps even invite the sweet surrender of sleep. 13.8 billion years ago. Imagine that number. It stretches beyond our grasp, a timeline so immense it almost feels fictional. Yet, this is the whisper of science, the grand narrative of our cosmos. In one fleeting, impossible moment, there was nothing. And then, in the very next, there was everything. Try to feel the weight of those words, the profound shift from absolute void to boundless existence. Just how this could be possible. How this transformation from an unimaginable nothingness to a universe teeming with stars, galaxies, and perhaps even life occurred. Remains perhaps the biggest question in all of science. It's a question that gracefully dances across the boundaries between what we can observe and what we can theorize, between the cold, hard logic of physics and the deep, searching inquiries of philosophy. Every single thing we know about our universe, from the intricate dance of atoms to the sweeping arcs of galaxies, hinges on concepts we take for granted: mechanism, process, and causality. We are, by our very nature, creatures who strive to understand reasons. We want to know why the sky is blue, why the tides rise and fall, why we exist. We search for the intricate chain of events that leads from one state to another, always seeking the cause behind every effect. And yet, when we reach the very foundational layer of existence, at the most fundamental level, we find ourselves at a loss. We simply do not know how or why the entire universe came to be. This isn't for a lack of trying, though. Generations of brilliant minds have dedicated their lives to peering into this cosmic mystery, to tracing the threads of existence back to their ultimate origin, perhaps. As the famed cosmologist Stephen Hawking once beautifully supposed, there truly was nothing before. This idea, at first glance, feels almost too simple, too direct. If we consider space and time not as external containers, but as inherent, conjoined properties of the universe we inhabit, then the very beginning of that universe marked the very beginning of time itself. Imagine a timeline stretching back, further and further. If time began with the universe, then before time, there could be no space. And if there was no space, then logically, there could be no universe. Hawking, with his profound insights, looked at the geometry of space-time, tracing its path backward through the ages. He saw it contracting, curving around itself, and eventually, rounding out into a smooth, self-contained surface. Think of it like the surface of a sphere, like our Earth. If you walk north from any point on Earth, you eventually reach the North Pole. But what happens if you try to go north of the North Pole The question itself loses all meaning, doesn't it? There's simply nowhere further north to go. In Hawking's vision, searching for something beyond the beginning of time would be just as meaningless. It would be like trying to find a point that is north of the Earth's North Pole. The concept of before simply wouldn't apply, because time, as we know it, wouldn't have existed. It's a concept that invites quiet contemplation, a gentle release from the need for a linear progression that our minds are so accustomed to. Or perhaps, the truth is even more elusive, and there was no actual beginning in the sense we typically imagine, but rather a limit to our powers of observation, a veil that our current understanding cannot yet pierce. Scientists often speak of a split-second period of exponential expansion, a cosmic growth spurt known as inflation. That truly put the bang in the Big Bang, this incredibly rapid expansion. Occurring in an unimaginably tiny fraction of a second, is thought to have set the stage for everything that was to follow, shaping the universe into the vast, expanding entity we observe today. Our inflation, the one that shaped our observable universe, is believed to have stopped after a tiny fraction of a second. But some physicists, in their boundless curiosity, have suggested that this wasn't the only period of inflation in the cosmos as a whole. Rather, they propose that inflation might continue elsewhere, eternally, like an unending process of cosmic birth. This continuous, eternal inflation could produce countless bubble universes, each one budding off and expanding, distributed throughout a potent, everlasting multiverse. Imagine an infinite ocean, constantly bubbling and frothing, with each bubble being a complete universe, with its own laws, its own stars, its own possibilities. Our universe. This vast expanse we call home could simply be one such bubble, floating gently within this grandeur. Infinite foam. It's a thought that can make the mind feel incredibly small, and yet, paradoxically, incredibly vast, encompassing so much more than we can ever perceive. Another captivating idea, one that offers a different rhythm to the cosmic dance, is the theory known as the Big Bounce. Instead of starting from an absolute nothingness and inflating exponentially to produce the intricate structure we see today, contemporary physicists like Paul Steinhardt suggest a cyclical growth and contraction of everything within the universe. Imagine a cosmic breath, an inhale and an exhale on a scale that defies imagination. In this view, our current universe isn't a singular event, but merely the latest in a long, and potentially infinite, series of expanding and contracting cosmos. The universe expands to a certain point. Then gravity, perhaps, begins to pull it back, contracting it into a dense hot state, only for it to bounce back out again, into a new cycle of expansion. It's a universe that perpetually renews itself, a timeless cosmic dance without a true beginning or end. This gentle rhythm, this idea of endless cycles, can be deeply comforting, suggesting a cosmic resilience, a never-ending story, or perhaps our understanding of scale itself is fundamentally incomplete. Physicist Roger Penrose, with his brilliant mind, considered the properties of shapes regardless of their size. He believed we could apply a similar concept to the cosmos. In his intriguing idea, the universe loses its sense of time and scale at the infinitely small and the infinitely big. Imagine a point, almost too tiny to conceive, and then imagine an expanse so vast it swallows all thought. Penrose suggests that at these extreme edges, the universe becomes, to all intents and purposes, equivalent. Think of a game of chess, whether it's played on a tiny board that fits in your pocket or a monumental one that spans an entire courtyard. The rules remain precisely the same. The pieces move in the same way. The strategies hold true. The scale changes, but the fundamental nature of the game does not. Could our universe operate on such a principle? where the smallest and largest aspects echo each other in ways we are only just beginning to grasp. It's a thought that blurs the lines between what is grand and what is minuscule, inviting a sense of unity in the vastness. Then there is the possibility that our cosmos came about as a transient collision of dimensions. This idea often emerges from the intricate tapestry of superstring theory, which attempts to explain the very fundamentals of reality not as tiny, point-like particles, but as minuscule vibrating strings. These strings exist within an 11-dimensional reality of hyperspace, far beyond the 4 dimensions of space and time that we readily perceive. The 3 dimensions of space and 1 dimension of time that we experience within our cosmos are, in this view, merely a single brane, a fundamental, higher dimensional object in the overall bulk of this grander reality, the beginning and subsequent growth of our universe. In this captivating scenario, could have simply come about as higher-order branes collided, like immense, cosmic membranes rippling and touching within a vast, unseen ocean. Imagine 2 enormous, invisible sheets in some higher dimension, drifting through infinity, and then, with a gentle, imperceptible brush, they touch. That touch, that transient collision, could have been the spark that ignited our entire universe. Creating the Big Bang and all that followed, it's a vision that expands our minds beyond the familiar, inviting us to consider realities far richer and more complex than our everyday experiences allow. And perhaps, just perhaps, there is something else entirely, some hidden corner of mathematics or physics that we have yet to shine a light into. A profound truth that, for the time being, entirely eludes our understanding. It's a humbling thought, isn't it, to acknowledge the vastness of what we don't yet know, to accept that our current theories, while incredibly powerful, may only be scratching the surface of cosmic truth. For now, our universe's origin story remains a mystery, a cosmic multiple-choice quiz where we are still searching for the right answer. Or perhaps for new questions entirely. It's a choose-your-own-adventure story written in the stars, with countless paths yet to be explored. Nevertheless, despite all the mysteries, all the intriguing possibilities, one thing remains certain: 13.8 billion years ago, the universe did begin. This is not a guess, but a conclusion drawn from a mountain of evidence, from the faint echoes of the Big Bang itself, to the expansion of galaxies, to the abundance of light elements. This certainty, this profound knowledge, anchors us in the midst of all the grand speculations. And this, dear friend, is the story of what happened next. This is where our journey truly begins, moving forward from that impossibly ancient moment. Through the strange and wonderful epochs that shaped our cosmic home, we will wander through the incredibly hot beginnings, the emergence of forces, the formation of the first light, and the slow, majestic dance of creation that continues even now. There's no rush, no pressure, just the gentle unfolding of a story that is, in its essence, the story of everything. Let your mind float freely as we explore these wonders together, allowing the vastness of these ideas to soothe and calm you, guiding you towards a restful stillness. Let us journey now, beyond the abstract, into the tangible, yet still astonishing, realm of cosmic extremes, as our minds gently drift, carried by the quiet current of curiosity. Let's ponder a question that seems, at first glance, quite simple. Where is the hottest place in the universe? Your mind, perhaps, might immediately conjure images of a fiery furnace, a natural fusion reactor at the very heart of a star. And indeed, stars are unimaginably hot, even as you imagine incinerating in a hypothetical plunge through their fiery depths. Your journey would, surprisingly, be in vain if your quest was for the absolute peak of cosmic temperature. The temperatures at the core of our own sun, for instance, reach a mere 15 million degrees Celsius, That is, of course, an unfathomable heat by any earthly standard, enough to fuse atoms and power entire planetary systems. But it is far from the universe's most extreme inferno. You might then turn your gaze towards even more violent phenomena in the cosmos. Events of cataclysmic power and breathtaking scale, like explosive supernovae. Here, during the dramatic, spectacular death of a colossal star, its core collapses, triggering a colossal explosion that ejects superheated shells of gas, hurtling them across many light years in every direction. What remains at the heart of this cosmic fireworks display is often a gravitationally compactified neutron star, a remnant so dense that a teaspoonful would weigh billions of tons. Temperatures within the immediate vicinity of such an event, in the shockwaves of the dying star, far exceed normal stellar furnaces, reaching a staggering 100 billion degrees Celsius. This is a temperature that utterly dwarfs the heat of a stellar core, a blistering inferno that vaporizes anything in its path. Yet, astonishingly, this still isn't the hottest temperature to be found in the vast expanse of creation. In fact, the highest temperature that has ever been recorded anywhere in our vast cosmos. This sweeping canvas of stars and galaxies was not found in the depths of space, but rather a mere 100 meters beneath the snow-covered ground near the tranquil shores of Lake Leman, in Switzerland. And this extraordinary temperature didn't come about from some colossal natural process, from the birth or death of stars, but rather from the concerted, deliberate efforts of hundreds of dedicated scientists, fueled by billions of euros worth of meticulous research and development. It was, quite literally, a man-made inferno, a fleeting glimpse into conditions that echo the very earliest moments of time. This incredible feat of temperature generation occurred within CERN's Large Hadron Collider, a monumental underground ring where individual particles are routinely accelerated to velocities approaching the speed of light. Imagine tiny specks of matter, far too small to ever see, being hurled around a 27-kilometer tunnel, gaining unimaginable energy. In a particularly notable experiment in 2012, two lead atoms, themselves incredibly tiny, were smashed into one another with such immense force, such incredible energy, that their collision briefly produced a temperature of around 5.5 trillion degrees Celsius. To put that into perspective, it was 50 times hotter than the heart of a supernova. For a fleeting instant, within that controlled environment, humanity recreated a miniature version of the universe's fiery infancy. But even this astounding achievement, this terrestrial inferno, is still not even close to the highest possible temperature. Temperature, in its most fundamental sense, is little more than a manifestation of a particle's energy, its motion, or how fast it is vibrating. Think of molecules bouncing around, jiggling and trembling. The faster and more energetically they move, the hotter something is. Conversely, absolute zero, marking 0 Kelvin, which is equivalent to 273.15 degrees Celsius, represents the lowermost limit. At this theoretical extreme, particles would, hypothetically, come to a complete, shuddering stop, utterly devoid of all thermal energy were it possible to actually reach this elusive state. But if there's a lower limit, a chilling stillness, then logic whispers that there must also be an upper limit too. This upper boundary is often referred to as absolute hot. It marks the highest conceivable temperature before the very fabric of existence. The particles themselves are torn apart by their own unimaginable energy. This ultimate, impossibly blistering temperature is known as the Planck temperature, and it is around 1.4 times 10 to the 32 Kelvin. To truly grasp the magnitude of that number is to invite the mind to stretch and expand, to touch the very edge of what is physically possible. Max Planck, the dedicated German theoretical physicist who gave his name to this unfathomably high temperature, found his academic stride around the beginning of the 20th century. His groundbreaking ideas are widely seen as the foundational blocks of quantum physics, a revolutionary branch of science that delves into the strange and counterintuitive world of the very small. It was Planck who first theorized the quantization of light, proposing that light energy isn't a continuous wave, but rather comes in discrete, indivisible packets, or chunks, which he called photons. This radical concept fundamentally changed our understanding of energy and matter. But Planck's insights didn't stop there. His work on photons, and his eponymous Planck constant, a fundamental constant of nature derived from his studies of electromagnetic radiation, led him to consider the fundamental quanta, the smallest possible units, of other natural phenomena as well, using such universal qualities as the speed of light and the force of gravity in combination with his own constant. He defined the Planck length. This is considered the smallest quantum of distance, an unimaginably tiny measurement of around 1.6 times 10 to the minus 35th meters. To give you a sense of scale, this is approximately 100 quintillion times smaller than a proton, a particle already so minuscule it exists beyond our everyday perception. The time it takes for light, the fastest thing in the universe. To travel this minuscule Planck distance through a vacuum is known as the Planck time. It amounts to an almost incomprehensible 5.39 44 seconds. This is the smallest unit of time that has any physical meaning within our current understanding. And finally, the Planck temperature, that practical measure of absolute heat, is the temperature at which the wavelength of thermal radiation reaches the Planck diameter. It can go no smaller. It is the point where our conventional understanding of temperature, as the average kinetic energy of particles, begins to break down, where energy itself becomes so concentrated that it affects the very fabric of space-time. It is no fair reflection on the human brain to say that these numbers, these unfathomable scales of the unimaginably small and the unimaginably large, are beyond our true comprehension. Our minds, shaped by eons of evolution, are exquisitely attuned to scales that are relevant to us, to the world we can see, touch, and interact with. We navigate a world of meters and seconds, of temperatures we can feel and appreciate. And so, it may seem that these Planck units, these ultimate limits of smallness and vastness, are too small, or in the case of temperature, too large, to be of any practical use in our daily lives. But it is precisely when contemplating the immeasurably tiny moment at the very beginning of our immeasurably vast cosmos that these units truly come into their own. They become the crucial measuring sticks, the fundamental building blocks of our theoretical understanding of how everything began. Why are they so important, then, in that fleeting, ancient instant? Because our universe is expanding, becoming less dense, and has been doing so for all of its history. Imagine a balloon being slowly inflated. The dots on its surface move further apart. Similarly, the matter and energy in our universe are spreading out, thinning over time. Scientists don't know for sure if our universe as a whole is infinite or not, but if it is truly infinite, then it always has been. This suggests a fascinating, almost paradoxical idea. If the universe is infinite, then rather than starting as a single, infinitesimal point, it would also have begun infinitely large, but incredibly dense. And rather than growing in size over time, it would simply have become less dense, its infinite contents spreading out into an ever-expanding canvas. Our observable universe, however, is different. This is a crucial distinction. The observable universe is the only part of the universe we could ever see, or interact with, or could ever see and interact with us. It's a cosmic bubble, and its limits are set by the speed of light and the finite amount of time light has had to travel since the universe's birth 13.8 billion years ago. We are seeing light that has been traveling for billions of years to reach us, showing us what the universe looked like in the distant past. But as we mentally travel back in time, that observable part of the universe shrinks and becomes more compact. Imagine rewinding a cosmic film, everything drawing closer and closer, denser and denser, until eventually we get to a time, that elusive, extraordinary moment, when everything within what would become our observable universe was only a single Planck unit of time old, a single Planck length in diameter, and with all of our future observable universe compacted into such an unimaginably tiny space. The temperature of the whole cosmos, for that briefest of instants, sat squarely at Planck temperatures. This is the ultimate crucible, the absolute peak of heat and density. It may come as little surprise to learn that this moment, this 100 million trillion trillionths of a second after the very beginning of time and space, is known as the Planck era. It is a very strange time indeed, a time where our familiar notions of reality, of separate forces and predictable laws, begin to dissolve, where the universe was a place of extreme, almost unimaginable conditions. It is a time that pushes the boundaries of our comprehension, inviting us to contemplate a reality far removed from our everyday experience. Let this thought settle gently in your mind. The idea of all that we see, all that we know, compressed into a space smaller than the smallest thing we can imagine, blazing at a temperature beyond comprehension. In this stillness, perhaps, you can feel the quiet hum of existence, the gentle unfolding of the cosmic story, leading us from this fiery birth into the vast, cool expanse we know today, as our gentle journey through the cosmic past continues. Let's turn our attention to the forces that sculpt our reality, the fundamental undercurrents that dictate how everything interacts. In the cosmos today, this vast, sprawling expanse of stars and dust, everything we experience, from the gentle whisper of a breeze on your skin to the brilliant blaze of a distant supernova, is governed by certain immutable laws of nature. These laws, in turn, are ultimately controlled by the intricate interplay of four major forces. You're familiar with them, even if you don't consciously name them. There's the strong force, the silent, powerful glue holding atoms together, the weak force, a subtle player governing certain types of radioactivity, and the very processes that power stars. The electromagnetic force, the unseen hand distributing energy over vast distances, responsible for light and electricity, and, of course, gravity, the familiar pull that keeps our feet on the ground and galaxies bound together. Max Planck, the visionary physicist we spoke of earlier, had a profound insight at the end of the 19th century. He predicted that the strong, weak, and electromagnetic forces could be quantized. Imagine, for a moment, that these forces aren't continuous flows, but rather discrete, tiny, indivisible parcels of interaction. You can think of them, in a way, like particles of matter themselves. But instead of building blocks of mass, they are the fundamental carriers of interaction. These so-called messenger particles are fascinating. For the strong force, we have gluons, particles that literally glue quarks together to form protons and neutrons. For the weak force, there are the W and Z bosons, mediating the processes of radioactive decay. And for the electromagnetic force, we have photons, the very particles of light itself. But gravity, that most pervasive and seemingly intuitive force, is different. For centuries, gravity was simply understood as a pull, a mysterious attraction between objects with mass. Then, in the early 20th century, Albert Einstein, with his towering intellect and revolutionary insights, presented his general theory of relativity. This theory completely overthrew the classical, mechanical definition of gravity. Instead of a force pulling objects together, Einstein conceptualized gravity as the curvature of space-time, Imagine a vast, invisible fabric stretching throughout the universe. Massive objects, like stars and planets, create indentations or warps in this fabric, much like a bowling ball placed on a stretched rubber sheet. Other objects, instead of being pulled towards the bowling ball, simply follow the curves and dips created in the fabric of spacetime. Through countless large-scale experiments, from observing the bending of starlight around the sun to detecting gravitational waves rippling through the cosmos, general relativity has been verified time and time again. The gravity-induced curvature of spacetime is now recognized as an inherent property of the universe, a fundamental aspect of reality that affects all matter and energy within it. It is, in essence, the geometric stage upon which all cosmic dramas unfold. Therefore, during the Planck era, that impossibly hot and dense moment just after the universe began, long before any of the conventional laws of nature held sway in their familiar forms, it was gravity that was first to manifest. It was the initial sculptor, the primordial carver of the emerging spacetime. But herein lies a profound problem, a deep mystery that continues to puzzle the brightest minds. Everything we know about the workings of gravity today is based on Einstein's incredibly successful theory, general relativity. However, that theory is only truly tested and verified on larger scales, on the scale of planets, stars, galaxies, and the vast cosmic web. It describes the sweeping curves of spacetime that guide the dance of cosmic giants. During the Planck era, however, our entire observable universe was condensed into an area many trillion times smaller than a proton. Imagine all the galaxies, all the stars, all the empty space we see today, squeezed into a speck of existence smaller than the tiniest particle you can conceive. At these incredibly minute scales, general relativity simply does not help us understand what was happening. Its equations, so elegant and precise on grand scales, break down when applied to the infinitesimally small. Instead, the dynamics of the extremely tiny, the realm of individual subatomic particles and the fundamental quanta of energy, are governed by an entirely different set of rules: quantum mechanics. This is a bizarre and counterintuitive world, where nothing is ever quite where you expect it to be. In the quantum realm, the very act of observing a particle can change its outcome. Instead of dealing in absolutes, quantum physicists consider probabilities. Particles exist in a superposition of states, like a ghostly wave until measured, and nothing ever stays the same for long. There is an inherent jitteriness, a constant flux. Fortunately for us, this lawless, probabilistic quantum world only truly reigns on nanoscopic scales. Within the confines of atoms and their constituent particles, by the time we reach magnitudes that we're more familiar with the size of a dust mote, a grain of sand, or anything larger, the probabilistic weirdness of quantum mechanics largely averages out. The individual quantum jitters cancel each other, and the world appears solid, predictable, and classical, governed by the macroscopic laws of physics that we intuitively understand. But during the universally nanoscopic Planck era, there was no escaping the quantum everything. The entire observable cosmos was so incredibly small, so incredibly dense, that the probabilistic and uncertain nature of quantum mechanics would have been dominant everywhere. And herein lies the profound problem for understanding how things actually worked in that moment. General relativity and quantum mechanics are fundamentally incompatible with one another. They are two of the most successful theories in the history of science, each brilliantly describing its own domain. But they refuse to work together seamlessly when applied to the same extreme conditions. It's like trying to fit two pieces of a jigsaw puzzle together that belong to different pictures. So, researchers are still searching for a solution, a so-called quantum gravity theory that is able to reconcile these two titans of modern physics. Such a theory would properly describe how the Planck-era universe behaved, bridging the gap between the grand, smooth curves of space-time and the probabilistic, discrete jumps of the quantum world. Unfortunately, It is a question that cannot reasonably be tackled by experimental means in our current technological state. Consider the vast energies needed to produce and study the other force messenger particles inside collider facilities, like the LHC. Then consider the elevated plane that gravity occupies, defining all of spacetime itself to truly probe gravity during the extremes of the Planck era. It would take a particle accelerator roughly the diameter of our entire solar system to generate enough power. Such an endeavor remains, for now, far beyond our wildest dreams. But this does not stand in the way of theoretical speculation and extrapolation. Indeed, it encourages it, fostering a vibrant landscape of ideas. One idea suggests that, like the other fundamental forces of nature, gravity also is communicated by a messenger particle, a quantum unit of gravity that has come to be known as a graviton. If gravitons exist, they would mediate the gravitational force, carrying its influence across spacetime. However, gravity as a force is so much weaker than the others, unimaginably feeble in comparison to electromagnetism or the strong nuclear force, that its meager messenger would be practically impossible to detect with our current instruments. It would be like trying to hear a single whisper in the midst of a roaring waterfall. Another fascinating theory, known as loop quantum gravity, offers a very different perspective. In this view, physicists imagine the smooth and ever-changing geometry of spacetime, that fabric of reality we spoke of, to be ultimately pixelated on the very smallest scales, instead of a continuous, flowing sheet. Spacetime would be made up of tiny, discrete loops or networks. By rewriting Einstein's elegant equations of general relativity in terms of these lines, or loops instead of points, the calculations for gravity on a quantum scale become much more manageable. It's like switching from drawing with a single, continuous line to creating an image from countless interwoven threads, each one a fundamental unit of spacetime. This approach offers a way to quantize gravity without relying on the concept of gravitons, painting a picture of a granular rather than smooth spacetime, and perhaps the leading possible quantum gravity solution, one that continues to rumble away in the background of theoretical physics. Captivating many minds is string theory and its deeper manifestation, M theory. This theory, as we briefly touched upon, imagines the point-like particles of traditional physics not as tiny dots, but as one-dimensional, vibrating strings. It is the specific vibrational state of these incredibly tiny strings that defines what a particle is, whether it's an electron, a quark, or indeed, the elusive force of gravity itself. Different vibrational patterns correspond to different particles and different forces, and yet, in order to make the intricate mathematics of string theory work, it becomes necessary to involve no fewer than 10 or 11 dimensions. Imagine not just length, width, height, and time, but many more dimensions curled up so tightly, or folded in on themselves within the strings themselves, that we cannot perceive them directly, or in some variations, these extra dimensions are partitioned into 2 or 5-dimensional structures known as branes, the fundamental objects of an even more elusive overarching theory with a simple, mysterious moniker M. M theory is often considered the grand, unifying theory that might encompass all known forces and particles. A master key to unlocking the universe's ultimate secrets. Each of these hypotheses for how quantum gravity may actually work is more mind-bending than the last, rooted deeply in the abstractions of mathematics, almost impossible to visualize in our everyday three-dimensional minds. And yet, that is just what we are trying to do when we cast our minds back, to imagine the first fraction of a second of our universe during the Planck era. We are trying to paint a picture of reality at its most extreme, its most fundamental, its most mysterious. Ironically, it was in the 1950s, when the science of quantum mechanics was still very much in its infancy. That American theoretical physicist John Archibald Wheeler provided us with a tangible, though highly conceptual, description of conditions in that turbulent and confusing time. He imagined the early universe, specifically during the Planck era, to be composed of a bubbling and dynamic quantum foam. This quantum foam, as Wheeler so vividly described it, comes about directly because of the dynamical and unpredictable nature of interactions on the quantum scale. Remember Heisenberg's uncertainty principle, which tells us that we cannot simultaneously know both the precise position and momentum of a particle. This principle, when applied to the energy of empty space at the Planck scale, seriously compromises our ability to define length, time, or energy at any one point within the Planck-sized universe. The very fabric of space-time, which we usually perceive as continuous and coherent, is replaced by an inherently unpredictable and varying, foam-like texture that shifts and changes randomly, moment by moment. In this agitated foam, quantum micro-black holes, incredibly tiny, fleeting black holes, and wormholes hypothetical tunnels through space-time spring spontaneously into existence and then disappear without a trace. Without any apparent cause and effect, it is a realm where the rules of classical physics are utterly suspended, where reality itself is fluid and uncertain. In this highly energetic, supercompact, and miniaturized cosmos, for the briefest of moments, anything goes. It is a place of ultimate chaos and boundless potential, a primordial soup of quantum fluctuations. But after only 100 million trillion trillionths of a second, an almost incomprehensibly short span of time. Yet still an after in the context of the Planck era, the widespread unpredictability of the Planck era begins to come to an end. As the universe undergoes a gradual, infinitesimal growth and a slight cooling, it heralds a new epoch, a new chapter in its grand story. The conditions begin to soften, to crystallize. Ever so slightly, the universe won't look or behave anything like it does today for a while yet. It is still unimaginably hot and dense, a place unlike anything we can readily picture. But from here on out, from this point of gentle cooling and subtle expansion, our current theories do at least stand a chance of describing what is going on. The chaos begins to subside, and the first hints of order begin to emerge from the quantum foam. It's a slow, majestic transition from the utterly unknowable to the realm of the partially understood, a testament to the universe's ceaseless journey from simplicity to complexity. Let your mind linger on this transition, this quiet shift, as the universe itself begins to breathe a little more deeply, moving from a dreamlike state into a more defined reality, as the universe gently eased out of the Planck era's tumultuous embrace, moving from that chaotic quantum foam towards something more recognizable. The fundamental forces of nature began to emerge, shaping everything that followed. Today, in our everyday lives, everything we experience, every subtle interaction, every grand phenomenon, is controlled and defined by these four fundamental forces of nature. Let's take a quiet moment to truly appreciate them, to see how profoundly they weave through the fabric of our existence. Even in the simplest of actions, imagine, for a moment, that you are settling down for a quiet evening. Perhaps you're on a soft, comfortable couch, ready to watch something on television. Gravity is the unseen hand that keeps you pinned firmly to the seat of your chair. A constant, comforting pull that connects you to the earth. It's the same force that holds our planet's life-sustaining atmosphere close to its surface, preventing it from dissipating into the cold vacuum of space, and its gravity too. That holds the Earth in its majestic orbit around our nearest star, the Sun, providing that stable, consistent warmth and light that creates a habitable environment for your continued existence. Yet, despite its colossal reach and universal influence, gravity is remarkably weak on a personal scale. You can overcome it with the muscles of a single arm, effortlessly lifting the remote control to change the channel. This contrast between its universal power and its localized gentleness is one of its quiet mysteries. In response to your button press, an invisible beam of infrared light, a form of electromagnetic radiation, beams across the living room from the front of the remote. It's a silent, unseen messenger carrying your command. Then, the picture comes to life in front of you. A vibrant display brought forth by millions of tiny pixels, each one emitting visible light, another form of electromagnetic radiation. This light travels back across the room, gracefully entering your eyes. Painting images on your retina, your eyeballs themselves are marvels of evolutionary innovation, intricate biological instruments designed to capture and interpret light. But at their core, their very function, indeed their very existence, relies on the properties and behaviors of the atoms within them. And these atoms, the electrons dancing around their nuclei, are held together by the elegant, ubiquitous electromagnetic force. It is this force that dictates how light interacts with matter, how chemical bonds form, and how electrical signals travel through your nerves. Without it, there would be no light, no sight, no coherent matter to even form your eyes. Digging even deeper into the heart of those atoms, we find the nuclei themselves, tiny, dense clusters held together by an even more powerful force, the strong nuclear force. Protons and neutrons, packed tightly together in the center of the atom, are bound by this incredibly potent pull. It is the strongest of all the fundamental forces, operating only over incredibly short distances. Within the very core of atoms. Not only that, but these protons and neutrons are themselves made up of three smaller subatomic particles, called quarks, which are also bonded by the same immense pull of the strong force. Every atom in your body, every atom in the television, every single atom in existence itself, relies upon this force for its stability and integrity. It is the invisible architect of all matter, a silent, powerful guardian of solidity. As your eyes focus and you engage with the pictures moving on the screen in front of you, each of the nerves inside your brain fires at an astonishing rate, up to 200 times per second. All of that coordinated electrical potential, that intricate dance of neural activity that forms your thoughts and perceptions, relies on a proper balance of potassium within your body. Like the other elements, potassium is held together by the strong nuclear force, but there is something else at play as well, a subtle undercurrent that affects its very nature. Because potassium is very slightly radioactive, and around 5,000 potassium atoms radioactively decay every second within your body, a decay driven by the weak nuclear force, and 150 million kilometers away. The core of our sun burns with the unimaginable heat of a stellar furnace, powered by the continuous fusion of hydrogen into helium. This incredibly powerful reaction, a controlled nuclear process on a cosmic scale, is responsible for the heat that keeps the Earth habitable, that allows life to flourish, and on a galactic scale. It's the weak nuclear force that plays a crucial role in creating the very elements that make up the planet, the television, and you. Without the weak force, stars wouldn't shine as they do. And the heavier elements, those building blocks of planets and people, wouldn't be forged in the cosmic fires. It may be weak in name, but it is mighty in its reach. A quiet, powerful force enabling the creation of new matter across the universe. Each of these four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, act together in intricate harmony to shape our experiences of the universe. And so it has been for the majority of our cosmos's multi-billion-year history, a steady symphony of interactions. But in the very first moments of time, immediately following the Planck era, conditions conspired to craft a very different set of rules, derived from the same basic physical ingredients. During the Grand Unification epoch, which followed the Planck era, there weren't four distinct forces, but only two. How could this be the case? How could forces we now perceive as separate have once been intertwined? The key to visualizing this lies in a simple, familiar act, a coin toss. Imagine you're about to flip a coin to decide between two equally weighted choices. Perhaps heads for one team, tails for the other. The decision, the clear outcome, is only reached when the coin settles after the flip, when the energy provided by the flexing of your thumb and forefinger is completely spent, and the disc comes to a definitive rest, revealing one clear face. Before that point, when the coin is still imbued with energy, spinning rapidly through the air or across the table, it is nigh on impossible to even distinguish its two faces. The two choices available to you, there is just a single spinning orb, a blur of motion, with characteristics all of its own, neither truly heads nor truly tails. This fascinating analogy helps us understand what we encounter when we examine the behaviors of the fundamental forces at higher energies, the extreme. Concentrated energies that were present in the nascent universe. When you increase the temperature dramatically, injecting vast amounts of energy into the system, the individual properties of the weak nuclear force and the electromagnetic force begin to weaken and blur into one another. It's as if the coin is spinning so fast. Its two distinct sides merge into a single, unified blur. We no longer see the distinct heads of electromagnetism and the tails of the weak force, but rather the spinning, faceless force of the two united the so-called electro-weak force. This unification has actually been experimentally confirmed in particle accelerators, where sufficiently high energies can reveal this merged nature. Now, imagine increasing that energy even further, to temperatures far beyond anything we can achieve today, temperatures that existed just after the Planck era. The spinning coin concept again applies, but this time to the strong force and the electroweak force, with high enough temperatures. These two begin to blur into a single unified whole, in a process known as grand unification. This ultimate unification of three of the major fundamental forces gives rise to what is sometimes known as the electro-strong force. It's a compelling idea, suggesting a deep underlying unity to nature's fundamental operations. However, while this tidy, spinning coin theory of grand unification is incredibly elegant, it has yet to be definitively proven experimentally in its entirety. Even though the energetic collisions inside particle accelerators can clearly point us towards the joining of electromagnetism and the weak force, it would take energies some million times greater for the strong force to lose its identity and merge in the same way. Even the most energetic phenomena in the universe today, like the explosive power of supernovae and the colossal jets emitted from the poles of black holes, are still a million times too feeble to reach the energy levels required for this grand unification. It's a testament to the extreme conditions of the early universe, conditions we can only barely glimpse in our most powerful laboratories. And as for weather gravity, the fourth fundamental force is ever accepted into this unified fold, whether it, too, was once indistinguishable from the other forces at even more extreme energies. That is a profound question for the mysterious and unpredictable Planck era itself. And yet another problem for the contending theories of quantum gravity to address. It remains the ultimate puzzle, the final piece in the cosmic jigsaw. Still, the grand unification theory, as it is known, is a strong contender for explaining the workings of the universe just after the Planck era, offering a compelling narrative of unity emerging from diversity. For a period of time some 10 million times longer than the entire Planck era, the universe expanded and cooled. This might sound like a long time, but it is testament to just how incredibly small everything started out. That, even by the end of this epoch, the entire cosmos was still smaller than a single quark, the smallest particle of matter known today. Imagine all of existence, all the potential for galaxies and stars. condensed into something tinier than the most fundamental building block of matter, with the latent energy of that cosmos compressed into such an impossibly tiny space. The temperature reached an astonishing 100,000 trillion Kelvin. To give you some context, this is some trillion times higher than the Large Hadron Collider has ever managed to achieve, making even our most powerful scientific instruments seem quaint in comparison. These were the utterly extreme conditions that defined the grand unification epoch, a realm ruled by the chimeric electrostrong force and the bizarre, fluid interactions that it brings about in this minuscule, super-hot cosmos. Particles were undergoing an extreme identity crisis. The very concept of stable matter, as we know it, was fluid, photons, the massless particles of light, would transform spontaneously into matter-antimatter pairs, momentarily creating quarks and leptons, only for these nascent particles to be desperately short-lived, decaying rapidly back into photons scarcely as soon as they had formed. The electrostrong messenger bosons, the carriers of this unified force, only serve to complicate the picture further, facilitating an endless dance of transformation, helping quarks to transform into leptons, leptons into quarks, matter into antimatter, and vice versa, under the chaotic, unified rule of grand unification. It was a free-for-all of energy and matter, of particles both virtual and real, constantly appearing, disappearing, and changing their fundamental nature, until a trillionth of a second after it began. The penny drops. The universe had expanded and cooled just enough. Temperatures plummeted to a mere 1,000 trillion degrees. Still unimaginable to us, but cool enough. Just cool enough. For a momentous event to occur. For the strong force, that mighty glue, to finally break free from its unified embrace. For two forces to become three, and with that gentle yet profound separation. Everything changes once again, setting the stage for the universe we now inhabit. It's a moment of cosmic differentiation, a subtle shift that allows the familiar forces to begin their independent dance, laying the groundwork for the complexity and structure that will eventually emerge. Let this image of separation, of new distinctness, settle softly in your mind as the universe takes another step away from its unified, fiery past, and yet, as compelling and elegant as these theories of cosmic origins and fundamental forces are, there is a subtle whisper, a quiet reservation that still lingers. While these theories may adequately describe the behavior of particles within the earliest moments after the Big Bang, they fall short of explaining the large-scale cosmos that will eventually come to exist. When we compare the starting conditions, as dictated by these profound ideas, with the universal end result, the vast, intricate, and remarkably uniform universe we observe today, the Big Bang, in its simplest form, appears to be, in certain crucial ways, broken. There are pieces missing from the cosmic jigsaw puzzle, and these omissions pose deep, thoughtful questions that continue to guide our exploration. Let's turn our gaze, for a moment, to the recent past, to a truly awe-inspiring technological marvel. By July 2022, the iconic James Webb Space Telescope was well established in its distant orbit around the Sun. A silent sentinel positioned 1.5 million kilometers out in space, following a nail-biting, month-long journey and a meticulous phase of deployment and calibration that lasted almost a year. Its 18 golden mirrors, perfectly aligned, were finally ready to begin their scientific operations in earnest. The world held its breath, anticipating the secrets it might unveil, but when it focused its magnificent gaze into some of the deepest reaches of the observable universe, peering back in time further than ever before, scientists were, quite simply, shocked. After seeing the images returned from this revolutionary telescope, American astrophysicist Alison Kirkpatrick, a brilliant mind in the field, wrote in the scientific journal Nature, with a touch of profound honesty, that she found herself lying awake at 3 in the morning, wondering if everything she had ever done was wrong. Within a month, these images and Kirkpatrick's candid comments had taken on a life of their own, spreading like wildfire across the scientific community and beyond. The fixed, unchanging speed of light means that the deeper we peer into space, the farther back in time we are looking. It's like a vast, cosmic time machine, and at distances corresponding to just 200 million years after the very beginning of everything, an astonishingly early point in the universe's 13.8 billion year history, the James Webb Telescope had already seen fully formed galaxies. Not only that, but these galaxies were ordered with much more structure, more maturity, than anyone had thought possible at such an early epoch. Existing theories of star and galaxy formation simply had no way to explain it. They predicted a much more chaotic, less developed early universe. And it was this that Kirkpatrick had been so concerned about. This unexpected precocity of early cosmic structures, unfortunately. Soon her genuine scientific concerns had been extrapolated, twisted, and sensationalized by some media outlets, who claimed that the next generation telescope had disproved the landmark Big Bang theory with its very first images. This, of course, caused quite a stir, a ripple of alarm among those who follow cosmic discoveries. Thankfully, those concerns were misplaced. Kirkpatrick had only been concerned about existing theories on galaxy formation, the specific processes that build these stellar islands, not the entire cosmos creation event itself. The inexplicable structuring of early galaxies simply meant that there was a piece missing from our understanding, a gap in our knowledge about how galaxies assemble so quickly. Not that everything we knew about the Big Bang was wrong. It was, in essence, little more than a storm in a cosmic teacup, a misunderstanding amplified by the desire for dramatic headlines. And so, the Big Bang, as the fundamental description of the universe's beginning, is safe from that quarter, for now at least. But as a complete explanation of how our modern universe came to be, the Big Bang theory, in its original, most basic form, has been under far more severe threat, and for much longer. These are profound challenges, deep enigmas that have puzzled cosmologists for decades, highlighting the need for something more. An additional chapter in the cosmic story. When we look at the large-scale structure of the universe as it is today, there are a number of phenomena that don't quite add up, phenomena that the basic Big Bang model struggles to account for. To begin with, consider the average temperature of the universe. Even though stars burn at several million degrees Celsius, and the vast empty space between galaxies shivers at just a few degrees above absolute zero. The average temperature that we observe in one direction of the sky is remarkably similar to any other direction. It is a precise 2.7 Kelvin, everywhere in the universe. Imagine this incredible thermal homogeneity extends across all 93 billion light-years in diameter of our observable universe. But how can this be? If the universe has been gradually expanding for nearly 14 billion years, then how can 2 points further than 14 billion light-years apart, that is, points that could not possibly have exchanged heat or information since the Big Bang, given the speed of light limit, have averaged out their temperatures to be so perfectly uniform? The fact that we see such thermal homogeneity now implies that there was thermal homogeneity back in the universe's earliest moments. And this fact seems wildly improbable given the nature of quantum fluctuations in the compactified early cosmos. In those unimaginably small, dense conditions, quantum mechanics dictates that there should have been tiny, random variations in temperature, like ripples on a pond. How could these ripples have been smoothed out across such vast, disconnected distances? This is famously known as the homogeneity problem, or the horizon problem. It's a quiet whisper, suggesting that something profound must have happened to smooth out these initial irregularities. But there is more. Einstein's general theory of relativity describes how massive objects create curves in spacetime, which then govern the movement and evolution of matter within that spacetime. Stars, galaxies, and black holes leave pinches and pockmarks in the local scale structure of spacetime, creating gravitational wells. But when we zoom out to a much larger, cosmic scale, those imperfections miraculously even out to leave a smoother, remarkably flat structure which, much like the average temperature of the cosmos, seems to vary very little. The universe, on the largest scales, appears flat. This concept of flatness has deep implications for the future evolution of our universe. Imagine the universe not as a flat surface, but as having an overall curvature. If the overall density of matter and energy in the universe is sufficiently great, spacetime will be what's known as positively curved, bending back on itself like the surface of a sphere. Think of the surface of a balloon in this scenario. Eventually, the collective gravity exerted by all the matter and energy in the universe will be enough to slow down and eventually reverse the trend of expansion, causing the universe to collapse back in on itself in a cataclysmic event known as the Big Crunch. It's a dramatic, fiery end, a reversal of the Big Bang. In contrast, if the overall density is much lower than a critical value, it will result in a negative curvature of spacetime, bending outwards in an open, saddle-like fashion. With this geometry, gravity will never overcome expansion, and the cosmos will continue to grow, thinning out and cooling forever, eventually becoming a cold, dark, and empty void in a scenario sometimes called the Big Freeze or Big Rip. Which of these overall geometries holds true has immense implications for the future evolution of our universe, defining its ultimate destiny. And so, it has been a major preoccupation of astronomers to try to precisely measure the overall curvature of the cosmos that we can see. And counterintuitively, astonishingly, it appears to be completely flat. The universe seems to exist right on the knife edge between positive and negative curvature, poised in a delicate balance, just like the horizon problem. The likelihood of this being the case by chance is incredibly small, tantamount to tossing a coin and having it land perfectly on its edge. Balancing there indefinitely, for obvious reasons, this profound puzzle has become known as the flatness problem. It suggests a fine-tuning so improbable that it demands a deeper explanation. And there is one additional problem that quietly blights our theories of the cosmos in the first trillionth of a second. This is the curious case of the missing magnetic monopoles. All through the universe, electrical charges exist in positive and negative pairs, like the proton and electron, canceling one another out to result in a stable, neutrally charged whole. In a similar way, magnets are always found with both a north and a south pole, with magnetic field lines flowing gracefully between them to produce a stable and balanced whole. If you break a bar magnet in half, you don't get a separate north pole and a separate south pole, you simply get two smaller magnets, each with its own north and south pole. However, while it is possible for both positive and negative electrical charges to be found alone, like in isolated protons or electrons, respectively, no such isolated poles exist for magnets, no matter where we look in the cosmos. No matter how deeply we probe, we have yet to find a lone magnetic monopole, a single north pole without its opposite south pairing, or vice versa. Theoretical predictions, based on the physics of the early, incredibly hot universe, suggest that such monopoles should have been produced in abundance, like cosmic leftovers from the grand unification epoch, but they are nowhere to be found. This absence, this striking void where something should exist, is known as the magnetic monopole problem. So, it was on a quiet December night in 1979, while puzzling over the profound mystery of these missing monopoles, that theoretical physicist Alan Guth struck upon a truly remarkable solution, a solution so elegant, so encompassing, that it not only addressed his own specific problem of the missing monopoles, but also almost as a cosmic bonus, tackled the seemingly intractable horizon and flatness problems as well. It was a moment of profound insight, a quiet revolution in our understanding of the universe's earliest moments. Instead of expanding gradually over billions of years, from a point-like state to the unfathomable vastness we see today, Guth found a mechanism by which the universe could have suddenly and almost instantaneously inflated to many times its original size, before then slowing down and continuing its more linear, gradual expansion that we observe today. This proposed inflationary period would be a cosmic growth spurt of unimaginable speed and scale. Guth suggested that the universe would have doubled in size around 90 times in less than a trillionth of a second, resulting in an exponential expansion that would fundamentally change the face of the cosmos. Why is this exponential expansion so significant? Because when exponential expansion is at play, things get very large very quickly. To truly grasp the power of this, let's consider a familiar, yet astonishing analogy: folding a gigantic piece of paper in half. Time and time again. Imagine starting with a piece of paper incredibly thin, perhaps 1/10 of a millimeter in thickness. The first fold will double that, to 2/10 of a millimeter. The next fold brings it to just under half a millimeter. A third fold doubles it again, and now it is about the thickness of a fingernail. So far, so unremarkable. Nothing truly astonishing. But by the time you reach 7 folds, the single sheet of paper has now reached the thickness of an entire notebook. 10 folds, and it will be as thick as your hand is wide. The world record for actually doing this experiment with real paper sits at just 12 folds. Achieved in 2002 when an American schoolgirl folded a piece of tissue paper more than 1.2 kilometers in length into a bundle over half a meter thick. It's an incredible physical feat, pushing the limits of what a human can do, but if it were possible to make and handle an even bigger sheet, a cosmic sheet, further theoretical folds would increase the thickness astronomically. Defying all intuition, 23 folds will make the paper around 1 kilometer thick, reaching into the lower atmosphere, and 30 folds will be enough to get you to space. Rising 100 kilometers from the surface of the Earth, 42 folds will magically transport that paper all the way to the moon, reaching its surface from Earth, and a mere 51 folds will make it stretch all the way to the sun, touching the fiery heart of our star. Now, let's accelerate our cosmic folding. 81 folds will make the paper as wide as the Andromeda Galaxy, our nearest large galactic neighbor, stretching around 141,000 light-years across. And then, finally, imagine 90 folds. This astonishing number of doublings, equivalent to the 90 doublings that Alan Guth proposed for the inflationary period of our universe, would transform that single colossal piece of paper into a folded pile bigger than the entire Virgo supercluster, a vast assemblage of galaxies spanning 130 million light-years across. This incredible, almost unimaginable. Inflation is precisely what Alan Guth proposed for the entire universe, in less than a trillionth of a second. After the confusing turbulence of the Planck era and the subsequent grand unification epoch, the universe underwent this exponential growth spurt. It's a breathtaking idea, offering a powerful, elegant solution to some of the universe's deepest puzzles, and gently setting the stage for all the complexity and beauty that would eventually unfold. Let this image of the rapidly expanding universe fill your mind. A silent, swift growth that smoothed out imperfections and created the vast, flat, uniform cosmos we inhabit today. The rapid, almost instantaneous inflation, that period of exponential expansion following the Planck era and grand unification epoch, profoundly reshaped the early cosmos. It was as if the universe, in a mere flicker of time, stretched itself out, smoothing away any imperfections and preparing the stage for the intricate tapestry of stars and galaxies we see today. This concept, born from Alan Guth's profound insight, offers elegant solutions to the pressing puzzles we discussed earlier: the homogeneity problem, the flatness problem, and the curious case of the missing magnetic monopoles. Let's revisit the homogeneity problem, also known as the horizon problem. Remember how we wondered why the average temperature of the cosmic microwave background radiation, that faint echo of the Big Bang, is so remarkably uniform across the entire observable universe? 2 points, billions of light years apart, appear to have the same temperature, even though there hasn't been enough time since the Big Bang for light or heat to travel between them. It's like finding two distant islands in an impossibly vast ocean, each with the exact same temperature. Even though no wind or current could ever reach from one to the other, inflation offers a beautiful solution. Imagine, before inflation began, that the entire observable universe was infinitesimally small, a tiny speck of space-time. In this incredibly compact, dense state, all parts of what would become our vast observable universe were in intimate contact. They had ample time to exchange energy, to interact, and to reach a state of thermal equilibrium, where the temperature was uniformly distributed. Think of a very small, perfectly mixed cup of cosmic tea. Every part of it reaches the same temperature. Then, inflation happened in less than a trillionth of a second. This tiny, thermally uniform region of space-time was stretched and expanded to astronomical scales, far larger than our observable universe is even today. So, when we look out into the cosmos and see uniform temperatures across vast distances, we are essentially seeing the expanded remnants of that initial, perfectly uniform, incredibly small region. The homogeneity we observe isn't because heat had time to travel across billions of light years after the Big Bang, but because the universe was so small and well connected before inflation stretched it out. Inflation acted like a cosmic iron, smoothing out any wrinkles or variations that might have existed in that primordial soup, preparing a perfectly uniform canvas for the stars and galaxies to eventually form. It's a truly elegant explanation, painting a picture of cosmic preparation. Next, consider the flatness problem. Remember the perplexing observation that our universe, on the largest scales, appears to be perfectly flat, hovering precisely between the possibilities of positive and negative curvature. We compared it to tossing a coin and having it land perfectly on its edge. Without inflation, the universe would have needed to be exquisitely fine-tuned at the moment of the Big Bang, to an almost unimaginable degree of precision, to arrive at its current flatness. Any slight deviation from this perfect balance in the very early moments would have led to a wildly curved universe today, either collapsing back on itself almost immediately or expanding into a vast, empty, negatively curved expanse. Inflation provides a natural explanation for this uncanny flatness. Imagine you have an irregularly wrinkled piece of fabric, perhaps a large bed sheet that's been crumpled up. If you were to blow up a very small section of this sheet, inflating it to an enormous size, what would happen? That small section, no matter how wrinkled it was originally, would appear virtually flat from your perspective. The local curvature would be stretched out and smoothed away across the vast new expanse. Similarly, during the inflationary period, the universe expanded by a staggering factor of at least 10^26 and possibly much more in an incredibly short amount of time. This immense stretching effectively flattened out any initial curvature, any wrinkles in space-time that might have existed, no matter what its initial geometry was, whether positively or negatively curved. The inflationary burst would have expanded it to such an immense degree that, from our limited observational perspective, it would appear perfectly flat. It's like standing on the surface of an enormous, almost infinitely large balloon, even though the balloon is curved. Your immediate vicinity appears perfectly flat. Inflation, therefore, doesn't require an improbable fine-tuning of the initial conditions. It simply takes whatever curvature existed and stretches it into flatness. It's a cosmic magic trick, making the improbable seem inevitable. And finally, Let's consider the mystery of the missing magnetic monopoles. Remember how our theories predicted that these isolated north or south poles of magnetism should have been produced in abundance during the super hot conditions of the early universe, especially during the grand unification epoch yet. Despite exhaustive searches, we have never found a single one. This absence was a glaring discrepancy, a whisper of incompleteness in our understanding. Once again, inflation comes to the rescue with a simple, yet profound explanation. If magnetic monopoles were indeed produced in the very early universe, before inflation began, then the subsequent exponential expansion would have diluted their density across an unimaginable volume. Imagine sprinkling a handful of sand grains onto a small, deflated balloon. If you then inflate that balloon to the size of a city, those few grains of sand would become so incredibly spread out that you would be extraordinarily unlikely to find even one within any given observable region. In the same way, inflation stretched the universe so dramatically that any magnetic monopoles that were created would have been pushed so far apart, to such distant regions of space, that the probability of us observing even one within our entire observable universe becomes virtually zero. They are still out there, perhaps, but they are scattered so sparsely that they are effectively unobservable. Inflation doesn't deny their existence. It simply explains their scarcity within our cosmic neighborhood. It's a clever way to hide what should be abundant, resolving a deep theoretical puzzle with graceful simplicity. So, Alan Guth's theory of inflation, born from a seemingly isolated problem, provided elegant, interconnected solutions to three of the most significant puzzles facing the standard Big Bang model. It transformed our understanding of the universe's earliest moments, painting a picture not of slow, steady growth from the absolute beginning, but of a rapid, explosive transformation that set the stage for everything we see. But what caused this inflation? What was the engine behind this incredible cosmic expansion? The prevailing idea centers around a hypothetical quantum field, often called the inflaton field. Imagine, if you will, the entire universe, in its earliest, incredibly compact state, being permeated by this special field. Just as other quantum fields fill space and give rise to particles like the Higgs field, giving mass to particles, or the electromagnetic field giving rise to photons, the inflaton field would have been imbued with a tremendous amount of energy. When this inflaton field was in its high energy state, it generated a repulsive gravitational force. Yes, you heard that right. A repulsive gravitational force, pushing everything apart rather than pulling it together. This negative pressure, this outward push, was incredibly powerful, driving the exponential expansion of space itself. It's a mind-bending concept, the idea of gravity working in reverse, pushing the cosmos apart with incredible vigor as the universe expanded rapidly under the influence of the inflaton field. The field itself slowly rolled down to a lower energy state, much like a ball rolling down a gentle hill. As it reached the bottom of this hill, the energy stored within the inflaton field was then released, or decayed, converting its potential energy into a hot, dense soup of elementary particles and radiation. This sudden release of energy is what reheated the universe after inflation, filling it with the matter and energy we see today, marking the beginning of the conventional Big Bang hot phase. But with all the initial conditions beautifully set by inflation, this moment of reheating is sometimes poetically referred to as cosmic spring cleaning, or the graceful exit from inflation. It marks the transition from the rapid, empty expansion of inflation to the hot, particle-filled universe that we then continue to describe with the standard Big Bang model. This concept of an inflaton field, while still hypothetical, offers a compelling mechanism for inflation, grounding this extraordinary event in the principles of quantum field theory. It's a powerful idea because it explains how the universe could have started from conditions that, while extreme, didn't require improbable fine-tuning. Instead, a simple fundamental field with the right properties could have naturally led to the vast, smooth, and flat universe we inhabit. However, it's important to remember that inflation itself is still a theory, albeit a very successful one, with strong observational support while it elegantly resolves these deep cosmological problems. Direct experimental evidence of the inflaton field itself remains elusive. Scientists continue to search for the subtle imprints that inflation would have left on the cosmic microwave background radiation. Searching for specific patterns of gravitational waves that would be the smoking gun for this incredible cosmic growth spurt. The implications of inflation are vast and profound, stretching far beyond simply solving three cosmological puzzles. One of the most intriguing consequences is the idea of eternal inflation, which we briefly touched upon earlier. If the inflaton field doesn't decay uniformly everywhere at once, but rather randomly, it could mean that inflation might continue indefinitely in some regions of space, never quite ending. In these regions, new bubble universes could constantly be budding off, each with its own Big Bang, its own set of physical constants, and its own unique destiny. This takes us back to the concept of the multiverse. Our universe, the one we call home, with its specific laws of physics and its particular distribution of matter and energy, could simply be one bubble in an infinite, ever-generating cosmic foam. Imagine an endless, frothing sea of creation, where new universes are born in a continuous, graceful, and unceasing process. This idea profoundly changes our perspective on our own cosmic existence. It suggests that perhaps the apparent fine-tuning of our universe, where physical constants seem perfectly set for the emergence of life, isn't a miraculous coincidence, but simply a consequence of existing within a multitude of possibilities in an infinite multiverse. Every possible set of physical laws and conditions could be realized in some bubble universe. We simply find ourselves in one that allows for our existence. The concept of eternal inflation and the multiverse is a deeply philosophical one, raising questions about uniqueness, probability, and the very nature of reality. It's a thought that invites quiet contemplation, allowing the mind to expand beyond the confines of our single, familiar universe, into a realm of boundless cosmic possibilities. It's a way to embrace the uncertainty, to find comfort in the endless potential of existence. As you drift, let the idea of an infinite tapestry of universes, each unique, each a product of this incredible inflationary process, gently settle into your thoughts. There is a profound peace in recognizing the sheer scale and ingenuity of the cosmos, a peace that can guide you deeper into stillness. As the universe continued its incredible, rapid expansion, propelled by the unseen energy of the inflaton field, it was also undergoing a profound transformation. This immense cosmic growth spurt, while solving some of the most perplexing puzzles, also ushered in a new epoch, a critical transition from the rapid, empty expansion of inflation to the hot, dense, particle-filled universe that we can now describe with more conventional physics. This shift, a moment of cosmic reheating, marks the beginning of the universe as we generally understand it. A universe full of the fundamental particles that would eventually coalesce into everything we see. Imagine, for a moment, the end of that exponential growth, the point where the incredibly powerful outward push of inflation began to wane. It's like a colossal, invisible engine suddenly shifting gears, from an impossibly fast acceleration to a more steady, albeit still rapid, glide, as the inflaton field, that driving force, slowly rolled down to its lowest energy state. The vast amount of energy it had stored was suddenly, spectacularly, released. This colossal energy was then converted into a hot, dense soup of elementary particles and radiation. Think of it as an immense, cosmic furnace suddenly igniting, filling the void with light and matter. This moment, sometimes referred to as reheating or the graceful exit from inflation, wasn't a slow simmer but an instantaneous infusion of energy, transforming a nearly empty, rapidly expanding space into a buzzing, vibrant sea of fundamental constituents. This reheating was crucial. It provided the initial conditions for the Big Bang's hot phase to truly begin. But with all the initial conditions beautifully set by inflation, remember the horizon problem, the flatness problem, and the magnetic monopole problem. Inflation smoothed out the universe, made it flat, and diluted the monopoles. Now, with the universe uniformly hot and dense, filled with a primordial plasma of particles and antiparticles, the stage was perfectly set for the next acts of cosmic creation to unfold, following this reheating. For the next few incredibly brief moments, the universe was a place of astonishing extremes. The temperatures were still unimaginably high, far beyond anything we could ever recreate. This was the era of the electroweak epoch, a time when the electromagnetic force and the weak nuclear force were still unified as a single electroweak force. The spinning coin of these two forces was still spinning too fast for them to differentiate. Particles, in this super-energetic environment, were constantly colliding, transforming, and being created from pure energy. It was a chaotic, yet beautifully symmetric dance of fundamental interactions. As the universe continued to expand, ever so slightly cooling, a critical threshold was reached. At around 10-12 seconds after the Big Bang, when the temperature dropped to approximately 10-15 Kelvin, the electroweak force separated. This was the moment the coin slowed down enough to reveal its distinct sides. The electromagnetic force, responsible for light, electricity, and chemistry, became distinct from the weak nuclear force, which governs radioactive decay. This separation, a process known as spontaneous symmetry breaking, was a monumental event. It allowed particles to acquire mass through their interaction with the Higgs field, which also turned on around this time. Without this separation and the acquisition of mass, the universe would have remained a formless sea of massless particles, incapable of forming atoms, stars, or us. This moment of symmetry breaking is profound because it's where particles gained their identities, where the fundamental building blocks of matter began to truly take shape. Imagine a perfectly symmetrical snowflake forming. And then, as it grows, slight imperfections, slight differences, emerge that give it its unique character. Similarly, the universe, as it cooled, began to lose some of its initial perfect symmetries, allowing for the diverse and complex world we inhabit. After the electroweak epoch, the universe entered the quark epoch. This period, lasting from about 10-12 seconds to 10-6 seconds after the Big Bang, saw temperatures still incredibly high, but just cool enough for quarks and gluons to exist freely in a dense, hot plasma, much like a soup. Remember quarks, those tiny constituents of protons and neutrons in our present-day universe. Quarks are always confined within larger particles, never found alone. This is due to a phenomenon called color confinement, where the strong nuclear force, carried by gluons, binds them so tightly that it would require infinite energy to separate them. But in the quark epoch, the conditions were so extreme, so energetic, that this confinement hadn't yet fully taken hold. Quarks and gluons existed as a quark-gluon plasma, constantly interacting, transforming, and annihilating with their antiparticle counterparts. It was a vibrant, bubbling, subatomic stew, a dance of fundamental particles in a universe still incredibly small and dense. The strong force was at its most powerful, yet, paradoxically, it hadn't yet managed to fully bind these quarks into stable composite particles. Then, at about 10-6 seconds, or 1 microsecond, after the Big Bang, the universe had cooled enough for another crucial phase transition to occur. The temperature dropped to about 10-12 Kelvin, a trillion degrees Celsius. This was the critical point for the Hadron epoch to begin. At this temperature, the strong nuclear force became strong enough to finally confine the free quarks and gluons into more stable composite particles called hadrons, protons, and neutrons. The building blocks of atomic nuclei were formed during this time. Imagine the free-floating quarks suddenly snapping together, bound by the immense power of the strong force, forming the first stable particles that would persist into the future. However, this was still a chaotic environment. Hadrons, like protons and neutrons, were constantly colliding with their anti-particle counterparts, antiprotons and antineutrons, and annihilating each other, converting their mass back into energy photons in a perfectly symmetrical universe. This process would have led to a completely empty, radiation-filled cosmos, with no matter left over. But thankfully for our existence, there was a slight, almost imperceptible imbalance. For every billion antiparticles, there was approximately 1 billion and 1 particles. This tiny asymmetry, known as baryon asymmetry, is one of the universe's great mysteries and a key ingredient for our existence. This slight excess of matter over antimatter meant that after the vast majority of matter and antimatter annihilated, a small residue of matter remained. This precious leftover matter, born from a cosmic statistical fluke, is what makes up everything we see today: stars, galaxies, planets, and us. After the Hadron Epoch, which lasted for only a very brief time from about 10.6 seconds to about 1 second after the Big Bang, the universe had cooled further, reaching temperatures around 10.10 Kelvin, 10 billion degrees Celsius. At this point, the remaining hadrons, protons, and neutrons could no longer be formed from energy, and the vast majority of electron-positron pairs also annihilated, leaving behind a much smaller number of electrons. Alongside the much more abundant protons and neutrons, this marks the beginning of the lepton epoch, a time when leptons like electrons, muons, and neutrinos and their antiparticles dominated the mass of the universe. This epoch lasted until about 10 seconds after the Big Bang. Now, with the universe containing primarily protons, neutrons, electrons, and a vast sea of photons and neutrinos, the stage was set for a truly monumental event: Big Bang nucleosynthesis, BBN. This critical period occurred roughly between 3 minutes and 20 minutes after the Big Bang, when the universe had cooled to temperatures low enough from about 10.9 to 10.8 Kelvin for atomic nuclei to begin to form, but still hot enough to sustain nuclear fusion reactions. Imagine a cosmic cooking pot, still incredibly hot, but no longer boiling with the frenetic energy of particle creation and annihilation. At these temperatures, protons and neutrons, which had survived the annihilation with their antiparticles, could finally fuse together to form the nuclei of light elements. The simplest fusion involved a proton and a neutron combining to form deuterium, an isotope of hydrogen. Deuterium then combined with other protons and neutrons to form helium-4, the most common isotope of helium. A tiny amount of lithium was also formed. This process of Big Bang nucleosynthesis was incredibly efficient and precise. Theoretical predictions for the abundance of these light elements, hydrogen, helium, and lithium produced during BBN match observational data with remarkable accuracy. This agreement is one of the strongest pillars supporting the Big Bang model. It's like a cosmic fingerprint, left behind in the very composition of the early universe, perfectly matching our theoretical expectations. The universe, in these early minutes, was essentially a massive nuclear reactor, forging the basic ingredients that would eventually fuel stars and form the very first building blocks of complexity. After nucleosynthesis, the universe continued to expand and cool, but it remained a dense, hot plasma, protons, helium nuclei, and electrons were still free-floating, unable to combine into stable, neutral atoms because the temperature was too high. Photons, the particles of light, were constantly scattering off these free electrons, much like light trying to penetrate a very dense fog. This meant the universe was opaque to light. You couldn't see through it, because any photon would immediately bounce off an electron. Unable to travel freely, this period of cosmic opacity lasted for hundreds of thousands of years. Then, about 380,000 years after the Big Bang, a truly significant event occurred: recombination, or sometimes called decoupling. By this time, the universe had expanded and cooled sufficiently to about 3000 Kelvin. This temperature was low enough for electrons to finally combine with the protons and helium nuclei to form the first stable, electrically neutral atoms, mostly hydrogen and helium. Imagine the free electrons, which had been buzzing around like angry bees, suddenly settling down and being captured by the positive nuclei, forming the first stable atomic structures. This was a watershed moment because once electrons were bound into neutral atoms, they no longer scattered photons as readily. The cosmic fog suddenly lifted. The universe became transparent to light for the very first time. The photons that had been trapped, constantly scattering off free electrons, were now free to travel across the cosmos almost unimpeded. These photons, released at the moment of recombination, are what we observe today as the cosmic microwave background, CMB radiation. The CMB is perhaps the most compelling evidence for the Big Bang. It's a faint glow of microwave radiation coming from every direction in the sky, a direct relic of the universe's hot, dense infancy. When we detect the CMB, we are literally seeing the universe as it was, 380,000 years after the Big Bang. A baby picture of our cosmos. It carries with it the imprints of the tiny density fluctuations that were present at that time. Fluctuations that were the seeds for all the large-scale structure we see today, the galaxies, clusters, and superclusters. It's a profound thought, the faint hiss you might hear on an old analog television, or the subtle warmth emanating from every direction, is the afterglow of creation itself. A silent whisper from the dawn of time, from this point onwards, after the universe became transparent. The primary forces shaping cosmic evolution were gravity and the subtle interplay of matter and radiation. The universe entered the Dark Ages, a period lasting several 100 million years. During this time, there were no stars, no galaxies, and no other significant sources of light. The cosmos was filled with neutral hydrogen and helium gas, gently expanding and cooling. It was a period of profound cosmic stillness, a quiet interlude before the lights of the first stars would ignite. However, even in the darkness, gravity was subtly at work. The tiny density fluctuations imprinted in the CMB, those minute variations in the distribution of matter, began to slowly, inexorably, grow. Regions that were slightly denser began to attract more matter due to gravity, pulling in surrounding gas over vast spans of time. These small overdensities grew larger and larger, like invisible seeds slowly attracting cosmic dust. This slow gravitational collapse eventually led to the formation of the first structures in the universe, around 150 to 800 million years after the Big Bang. The first stars began to ignite, bringing an end to the cosmic dark ages. These were likely massive, short-lived stars, burning brightly and quickly, primarily composed of hydrogen and helium, the only elements available from Big Bang nucleosynthesis. Their intense ultraviolet radiation began to reionize the neutral hydrogen and helium gas in the surrounding universe, scattering the electrons free once more, but this time on a much larger scale, marking the epoch of rionization. As these first stars continued to form, they coalesced into the very first galaxies, drawing more and more matter into their gravitational embrace. These early galaxies were likely smaller and more chaotic than the grand spirals and ellipticals we see today. But they were the pioneers, the first islands of light in a still dark cosmos. They began to merge and grow, building up the larger structures we now observe, and so the story continues. From the incomprehensible temperatures and densities of the Planck era, through the delicate balance of matter and antimatter, the formation of the lightest elements, the cooling and transparency of the universe, and finally, the slow, majestic emergence of stars and galaxies, each step a testament to the fundamental laws of physics, guiding the universe from its simplest form to the complex, beautiful, and deeply mysterious reality we find ourselves in. Let these grand unfolding events gently settle in your mind, a narrative of cosmic becoming, easing you into a sense of profound peace and stillness, as our gentle exploration of the universe's past continues. From its fiery birth to the first glimmer of stars, we now arrive at the vast, dark expanse that emerged after the initial burst of light. This isn't the kind of darkness we know on Earth, but a cosmic quietude, a profound stillness stretching across immense spans of time. After the Big Bang nucleosynthesis forged the lightest elements, hydrogen and helium, and after the universe cooled enough for electrons and nuclei to finally combine into neutral atoms during recombination, something significant happened. The cosmos, now transparent to light, settled into a period known as the Dark Ages. This wasn't a time of literal nothingness, but rather a profound absence of the familiar brilliance we associate with the universe today. Imagine a vast, silent ocean, not yet stirred by the winds that will eventually bring forth waves. For several 100 million years, from about 380,000 years after the Big Bang until roughly 150 to 800 million years later, the universe remained in this state of profound cosmic night. During the Dark Ages, there were no stars, no galaxies, and no other significant sources of light as we understand them. The universe was filled predominantly with a vast, diffuse cloud of neutral hydrogen and helium gas. This gas, the raw material of future stars and galaxies, was gently, almost imperceptibly, expanding and cooling. It was a period of deep cosmic stillness, a quiet interlude, a long breath held before the universe's grand awakening. Think of a vast, empty canvas, waiting for the first strokes of paint to appear. However, even in this profound darkness, an invisible, persistent force was silently at work, weaving the threads of future complexity gravity. Remember those tiny density fluctuations imprinted in the cosmic microwave background? CMB radiation. The faint echoes of the Planck era's quantum jitters and inflation's smoothing touch. These weren't perfectly uniform. There were minute, almost imperceptible variations in the distribution of matter regions that were slightly denser than others, and regions that were slightly less dense. In the vast, silent canvas of the Dark Ages, these tiny fluctuations were the hidden seeds for all the large-scale structure we see today, over vast spans of time. Gravity began to inexorably act upon these slight overdensities. Regions that were infinitesimally denser began to exert a slightly stronger gravitational pull on the surrounding gas. Like invisible magnets, these denser pockets slowly, patiently, attracted more and more matter, drawing in the diffuse hydrogen and helium from their surroundings. This process was incredibly slow, almost imperceptible on human timescales, but relentless on cosmic ones. Imagine countless tiny, almost invisible wisps of cosmic dust, each slowly, gradually, drawing others towards it, building up tiny, imperceptible clumps. As these small overdensities continued to grow through gravitational attraction, they became larger and larger. The gas within these forming clumps became slightly warmer and denser. This slow gravitational collapse, this gentle pulling together of primordial gas, was the defining process of the Dark Ages. It was the universe laying the groundwork, patiently preparing for the emergence of light. Eventually, after hundreds of millions of years of this patient gravitational accumulation, the gas within the densest clumps became compressed enough that its core temperatures began to rise to extreme levels. And then, a truly monumental event occurred. Bringing the cosmic Dark Ages to a spectacular end, the first stars began to ignite. These pioneering stars, often referred to as population 3 stars, were likely very different from the stars we see today. They were probably massive, perhaps hundreds of times the mass of our Sun, and incredibly hot, because they were formed entirely from the pristine hydrogen and helium forged during Big Bang nucleosynthesis. They lacked any of the heavier elements like carbon, oxygen, or iron that are abundant in later generations of stars. This pure composition meant they burned their nuclear fuel much more quickly and intensely, living short, but incredibly brilliant lives. Their intense ultraviolet radiation, bursting forth into the long, silent cosmos, began to reionize the neutral hydrogen and helium gas in the surrounding universe. This was a reversal of the recombination event. The scattered electrons were once more set free from their atomic nuclei, but this time on a much larger scale. Marking the epoch of reionization, this was the universe beginning to light up from within, like scattered embers igniting into roaring fires. As these first stars continued to form, they naturally coalesced into the very first galaxies. These were not the grand, majestic spirals or elegant ellipticals we observe in the mature universe. Rather, they were likely smaller, more irregular, and more chaotic, still in their nascent stages of formation. But they were the pioneers, the first islands of concentrated light in a still largely dark cosmos. Imagine a few flickering candles in an immense, dark hall. Gradually multiplying and growing brighter, these early galaxies, driven by the relentless pull of gravity, began to merge and grow. Smaller galaxies collided and combined to form larger ones, creating the galactic structures we see today. This process of hierarchical formation, where small structures form first and then merge to create larger ones, is a cornerstone of modern cosmology. It's a dynamic, continuous process of cosmic construction, building complexity from simplicity over billions of years. This process of star formation, galaxy growth, and mergers continued. Within these evolving galaxies, new generations of stars were born, enriched by the heavier elements forged in the hearts of the first. Short-lived population 3 stars, when these massive early stars exploded as supernovae, they scattered their newly synthesized heavy elements, the cosmic dust of carbon, oxygen, iron, and countless others into the surrounding interstellar gas. This enriched gas then became the raw material for the next generation of stars, and critically, for planets, and eventually, for life itself. The very atoms that make up your body, the oxygen you breathe, the carbon in your cells, were forged in the fiery hearts of ancient stars, then scattered across the cosmos, patiently waiting to be incorporated into something new. As the universe continued to expand and cool, its overall temperature continued to drop. The cosmic microwave background radiation, once a blazing hot plasma, cooled to its current temperature of 2.7 Kelvin, a faint, uniform glow that permeates all space. Meanwhile, the large-scale structure of the universe began to solidify. Galaxies gathered into immense galaxy clusters, and these clusters, in turn, formed vast, interconnected networks of matter, known as the cosmic web. Picture an intricate three-dimensional web, with galaxies strung along its filaments like beads on a thread, and immense, empty voids in between. This cosmic web, the largest structure in the universe, is a direct consequence of those tiny initial fluctuations amplified by billions of years of gravitational attraction. Our own solar system, including our Sun, the Earth, and all the planets, formed much later, within one of these galaxies. The Milky Way, approximately 4.6 billion years ago, our Sun is a second or third generation star, meaning it was formed from gas and dust that had already been enriched by the remnants of earlier stars. This is why our Earth and our bodies are rich in heavier elements like iron, calcium, and silicon elements that were not present in the very early universe but were created through the cosmic alchemy of stellar evolution. So, The story of the universe is a grand narrative of transformation from the unimaginable density and heat of the Planck era through the rapid, smoothing expansion of inflation, the cooling and decoupling of forces, the formation of fundamental particles, the forging of the lightest elements in Big Bang nucleosynthesis, the long quiet of the Dark Ages, and finally, the slow, majestic emergence of the first stars, galaxies, and the intricate cosmic web. Each stage flowed seamlessly into the next, guided by the fundamental laws of physics, leading to the vast, complex, and beautiful cosmos we inhabit today. As you reflect on this incredible journey, let your mind wander through these immense scales of time and space, from the incomprehensibly small to the unimaginably vast, from the chaos of quantum foam to the ordered dance of galaxies. The universe has unfolded with a quiet, persistent elegance. There's a profound sense of peace in understanding that we are, in essence, made of stardust. Connected to this ancient, ongoing story, the universe continues to expand, to evolve, and to reveal new secrets, inviting us to remain curious, to continue to wonder, and to find stillness within its boundless mysteries. Let this deep connection to the cosmos bring you a sense of calm, a gentle drift into tranquility, as our gentle exploration of the universe unfolds. From its earliest fiery moments to the slow, majestic emergence of stars and galaxies, let us now turn our quiet contemplation to something both deeply personal and universally profound: time. It is an elusive concept. Isn't it? We feel its passage. We mark its moments. Yet it remains stubbornly difficult to define. Like trying to grasp smoke, we live within its relentless flow, from birth to growth, from present to past. But what is time? Truly, in the classical, Newtonian view of the universe, time was seen as an absolute, unyielding river, flowing uniformly and independently of everything else. It was simply there, a cosmic clock ticking away at a constant rate, providing an unchanging backdrop against which all events unfolded. Imagine a vast, perfectly synchronized clock, silently keeping rhythm across the entire cosmos, unaffected by anything that happened within it. This intuition, that time is a universal constant, is deeply ingrained in our everyday experience. We measure it with watches and calendars, assuming that a second here is precisely the same as a second anywhere else. However, in the early 20th century, Albert Einstein, with his revolutionary theories of relativity, profoundly reshaped our understanding of time. He revealed that time is not an independent, absolute entity, but rather a flexible, intertwined dimension, intimately connected with space, forming what we now call space-time. Imagine a vast, interconnected fabric, where space and time are not separate threads, but rather woven together into a single, dynamic tapestry. Einstein's special theory of relativity, published in 1905, showed us that time is relative. It means that the passage of time is not constant for everyone. Instead, it depends on the observer's relative motion. This phenomenon, known as time dilation, means that time can literally slow down for an object moving very quickly relative to another. Imagine a spacecraft traveling at a significant fraction of the speed of light. For an astronaut inside, time would pass more slowly than for someone remaining on Earth, while the astronaut experiences perhaps a few years. Decades might have passed on Earth. It's a mind-bending idea, suggesting that our individual experiences of time can differ dramatically depending on our journey through space. Then, 10 years later, in 1915, Einstein released his general theory of relativity, which deepened this understanding even further. He showed that time is not only affected by relative motion, but also by gravity. Massive objects, by curving spacetime, also warp the flow of time around them. This means that time passes more slowly in stronger gravitational fields. For instance, time literally runs infinitesimally slower on the surface of the Earth than it does in orbit, where gravity is slightly weaker. For objects with immense gravity, like black holes, time is warped to an extreme degree, slowing down almost to a standstill for an observer approaching the event horizon. This gravitational time dilation means that the cosmic clock does not tick uniformly for everyone. Its rhythm is subtly influenced by the distribution of mass and energy throughout the universe. It's a subtle yet profound truth. Time itself is part of the dynamic, ever-changing cosmos, not just a static background. So, if time is so flexible, so relative, what does that imply about the very beginning of the universe? The moment of the Big Bang. If space-time itself began at the Big Bang, then what can we say about before that moment? This question leads us into some of the deepest philosophical and scientific debates about the nature of time. Some physicists argue that the question, what happened before the Big Bang, is fundamentally meaningless, if time, as we understand it, emerged with the universe. Then there simply was no before. It's like asking what is north of the North Pole. The concept itself loses its coherence. In this view, time is an emergent property of the universe, not something that pre-existed it. Our intuitive desire to always trace things back to an earlier cause is a habit of mind shaped by our experience within time, not a reflection of a deeper cosmic truth. However, other theories propose that time might exist in some form even beyond our current universe, or that our universe is part of a larger, timeless reality. The Big Bounce theory, which we touched upon earlier, suggests a cyclical universe, where a previous universe collapsed into a dense state before bouncing back out into our current expansion. In this scenario, time might not have a singular beginning, but rather an endless series of contractions and expansions. This offers a comforting thought of cosmic resilience, a universe that perpetually renews itself, with time as an eternal, albeit fluctuating. Rhythm, similarly. The concept of eternal inflation in the multiverse also hints at a grander temporal landscape. If new bubble universes are constantly budding off from an eternally inflating background, then time might flow differently, or exist in different forms. Within that larger multiverse, our linear progression of time would be just one particular manifestation within an infinite sea of possibilities. It suggests that our experience of time, while deeply real to us, might be a localized phenomenon within a much vaster, more complex temporal reality. One of the most intriguing and mind-bending ideas about time comes from the realm of quantum gravity, particularly from approaches like loop quantum gravity. In this framework, space-time itself is thought to be quantized, composed of tiny, discrete loops or pixels. If space-time is granular at its most fundamental level, then time, as a component of space-time, might also be discrete, rather than continuous. This means that time might not flow smoothly, but rather jump from one tiny quantum of time to the next. It's like a film reel, where each frame is a discrete moment, and the illusion of continuous motion is created by showing them rapidly in sequence. This idea radically redefines our understanding of time's flow, suggesting a fundamental underlying choppiness to reality's most pervasive dimension. This perspective raises profound questions about the nature of existence. If time is truly quantized, does it ever stop? Does it have a smallest unit, beyond which nothing further can be divided? And what happens to our perception of continuous flow if reality is fundamentally discrete? These are the quiet, profound questions that whisper from the depths of theoretical physics, inviting us to reconsider our most basic assumptions about the world. Another profound idea suggests that perhaps time, at a fundamental level, doesn't actually exist in the way we perceive it. This concept often arises from attempts to unify quantum mechanics with general relativity in some quantum gravity theories. The equations that describe the universe do not contain a time variable in the traditional sense. This doesn't mean that events don't happen or that the universe is static, but rather that time might be an emergent property, a statistical phenomenon arising from the interactions of countless microscopic components. Imagine a vast, complex computer simulation. The underlying code might not explicitly contain a variable for time, but the interactions and changes within the simulation create the impression of time passing for an observer within that simulation. Similarly, our experience of time might arise from the changing configurations of particles and fields in the universe, rather than from a pre-existing, fundamental timer. This idea is deeply unsettling to our intuitive understanding, but it forces us to consider that our most familiar experiences might be mere manifestations of deeper, more abstract realities. Perhaps time is simply an illusion, a trick of consciousness, or a tool our minds use to organize the chaotic flow of events. This philosophical stance, often associated with block universe theory, suggests that all moments in time past, present, and future exist simultaneously, like frames in a film reel laid out side by side. Our perception of time flowing from past to future is merely our consciousness moving through these pre-existing moments, creating the illusion of progression. In this view, the future is as real as the past, and free will becomes a much more complex concept. It's a quiet whisper, inviting us to release our conventional grip on the linearity of existence as we gently drift through these profound concepts. Consider how our perception of time shapes our lives. We often feel rushed, pressured by deadlines, or yearning for moments past or future. But if time is truly this fluid, this deeply intertwined with space and gravity, and perhaps even an emergent phenomenon, then perhaps our rigid adherence to its linear progression is a human construct, not a fundamental cosmic truth. There is a deep peace in recognizing the uncertainty of time, in allowing our minds to float free from its relentless ticking. The universe, in its vastness, has already experienced countless eons, each moment unfolding with a quiet, patient elegance. Whether time began with the Big Bang, or whether it extends endlessly through cycles and multiverses, or whether it is an illusion, one thing remains: the present moment. This very moment, as you read or listen, is your anchor in the boundless ocean of existence. Let the whispers of these possibilities about time soothe your mind. There is no need to grasp a definitive answer, only to appreciate the profound mystery. Allow yourself to release the tension of the past and the anxieties of the future, and simply rest in the gentle embrace of the now. The universe is ancient and vast, and in its silent unfolding, time itself bends and weaves, a testament to the ever-changing, ever-mysterious dance of reality. Find comfort in this fluidity, and let it guide you into a deeper state of relaxation and stillness as our gentle exploration of the universe unfolds. From its earliest fiery moments to the slow, majestic emergence of stars and galaxies, let us now turn our quiet contemplation to something both deeply personal and universally profound: time. It is an elusive concept, isn't it? We feel its passage, we mark its moments, yet it remains stubbornly difficult to define. Like trying to grasp smoke, we live within its relentless flow, from birth to growth, from present to past. But what is time? Truly, in the classical, Newtonian view of the universe, time was seen as an absolute, unyielding river, flowing uniformly and independently of everything else. It was simply there, a cosmic clock ticking away at a constant rate, providing an unchanging backdrop against which all events unfolded. Imagine a vast, perfectly synchronized clock, silently keeping rhythm across the entire cosmos, unaffected by anything that happened within it. This intuition, that time is a universal constant, is deeply ingrained in our everyday experience. We measure it with watches and calendars, assuming that a second here is precisely the same as a second anywhere else. However, in the early 20th century, Albert Einstein, with his revolutionary theories of relativity, profoundly reshaped our understanding of time. He revealed that time is not an independent, absolute entity, but rather a flexible, intertwined dimension, intimately connected with space, forming what we now call space-time. Imagine a vast, interconnected fabric, where space and time are not separate threads, but rather woven together into a single, dynamic tapestry. Einstein's special theory of relativity, published in 1905, showed us that time is relative. It means that the passage of time is not constant for everyone. Instead, it depends on the observer's relative motion. This phenomenon, known as time dilation, means that time can literally slow down for an object moving very quickly relative to another. Imagine a spacecraft traveling at a significant fraction of the speed of light. For an astronaut inside, time would pass more slowly than for someone remaining on Earth. While the astronaut experiences perhaps a few years, decades might have passed on Earth. It's a mind-bending idea, suggesting that our individual experiences of time can differ dramatically depending on our journey through space. Then, 10 years later, in 1915, Einstein released his general theory of relativity, which deepened this understanding even further. He showed that time is not only affected by relative motion, but also by gravity. Massive objects, by curving spacetime, also warp the flow of time around them. This means that time passes more slowly in stronger gravitational fields. For instance, time literally runs infinitesimally slower on the surface of the Earth than it does in orbit, where gravity is slightly weaker. For objects with immense gravity, like black holes, time is warped to an extreme degree, slowing down almost to a standstill for an observer approaching the event horizon. This gravitational time dilation means that the cosmic clock does not tick uniformly for everyone. Its rhythm is subtly influenced by the distribution of mass and energy throughout the universe. It's a subtle yet profound truth. Time itself is part of the dynamic, ever-changing cosmos, not just a static background. So, if time is so flexible, so relative, what does that imply about the very beginning of the universe? The moment of the Big Bang. If space-time itself began at the Big Bang, then what can we say about before that moment? This question leads us into some of the deepest philosophical and scientific debates about the nature of time. Some physicists argue that the question, what happened before the Big Bang, is fundamentally meaningless. If time, as we understand it, emerged with the universe, then there simply was no before. It's like asking what is north of the North Pole. The concept itself loses its coherence. In this view, time is an emergent property of the universe, not something that pre-existed it. Our intuitive desire to always trace things back to an earlier cause is a habit of mind shaped by our experience within time, not a reflection of a deeper cosmic truth. However, other theories propose that time might exist in some form even beyond our current universe, or that our universe is part of a larger, timeless reality. The Big Bounce theory, which we touched upon earlier, suggests a cyclical universe where a previous universe collapsed into a dense state before bouncing back out into our current expansion. In this scenario, time might not have a singular beginning, but rather an endless series of contractions and expansions. This offers a comforting thought of cosmic resilience, a universe that perpetually renews itself, with time as an eternal, albeit fluctuating, rhythm. Similarly, the concept of eternal inflation in the multiverse also hints at a grander temporal landscape. If new bubble universes are constantly budding off from an eternally inflating background, then time might flow differently, or exist in different forms. Within that larger multiverse, our linear progression of time would be just one particular manifestation within an infinite sea of possibilities. It suggests that our experience of time, while deeply real to us, might be a localized phenomenon within a much vaster, more complex temporal reality. One of the most intriguing and mind-bending ideas about time comes from the realm of quantum gravity, particularly from approaches like loop quantum gravity. In this framework, space-time itself is thought to be quantized, composed of tiny, discrete loops or pixels. If space-time is granular at its most fundamental level, then time, as a component of space-time, might also be discrete, rather than continuous. This means that time might not flow smoothly, but rather jump from one tiny quantum of time to the next. It's like a film reel, where each frame is a discrete moment, and the illusion of continuous motion is created by showing them rapidly in sequence. This idea radically redefines our understanding of time's flow, suggesting a fundamental underlying choppiness to reality's most pervasive dimension. This perspective raises profound questions about the nature of existence. If time is truly quantized, does it ever stop? Does it have a smallest unit, beyond which nothing further can be divided? And what happens to our perception of continuous flow if reality is fundamentally discrete? These are the quiet, profound questions that whisper from the depths of theoretical physics, inviting us to reconsider our most basic assumptions about the world. Another profound idea suggests that perhaps time, at a fundamental level, doesn't actually exist in the way we perceive it. This concept often arises from attempts to unify quantum mechanics with general relativity. In some quantum gravity theories, the equations that describe the universe do not contain a time variable in the traditional sense. This doesn't mean that events don't happen, or that the universe is static, but rather that time might be an emergent property, a statistical phenomenon arising from the interactions of countless microscopic components. Imagine a vast, complex computer simulation. The underlying code might not explicitly contain a variable for time, but the interactions and changes within the simulation create the impression of time passing for an observer within that simulation. Similarly, our experience of time might arise from the changing configurations of particles and fields in the universe, rather than from a pre-existing, fundamental timer. This idea is deeply unsettling to our intuitive understanding, but it forces us to consider that our most familiar experiences might be mere manifestations of deeper, more abstract realities. Perhaps time is simply an illusion, a trick of consciousness, or a tool our minds use to organize the chaotic flow of events. This philosophical stance, often associated with block universe theory, suggests that all moments in time past, present, and future exist simultaneously, like frames in a film reel laid out side by side. Our perception of time flowing from past to future is merely our consciousness moving through these pre-existing moments, creating the illusion of progression. In this view, the future is as real as the past, and free will becomes a much more complex concept. It's a quiet whisper, inviting us to release our conventional grip on the linearity of existence as we gently drift through these profound concepts. Consider how our perception of time shapes our lives. We often feel rushed, pressured by deadlines, or yearning for moments past or future. But if time is truly this fluid, this deeply intertwined with space and gravity, and perhaps even an emergent phenomenon, then perhaps our rigid adherence to its linear progression is a human construct, not a fundamental cosmic truth. There is a deep peace in recognizing the uncertainty of time, in allowing our minds to float free from its relentless ticking. The universe, in its vastness, has already experienced countless eons, each moment unfolding with a quiet, patient elegance. Whether time began with the Big Bang, or whether it extends endlessly through cycles and multiverses, or whether it is an illusion, one thing remains: the present moment. This very moment, as you read or listen, is your anchor in the boundless ocean of existence. Let the whispers of these possibilities about time soothe your mind There is no need to grasp a definitive answer, only to appreciate the profound mystery. Allow yourself to release the tension of the past and the anxieties of the future, and simply rest in the gentle embrace of the now. The universe is ancient and vast, and in its silent unfolding, time itself bends and weaves, a testament to the ever-changing, ever-mysterious dance of reality. Find comfort in this fluidity, and let it guide you into a deeper state of relaxation and stillness. Let us now, in this quiet contemplation, shift our gaze from the grand cosmic dance of creation and the enigmatic nature of time, and gently turn towards something equally profound, but perhaps even more mysterious: the vast, silent, and largely unseen components of our universe. We have described the story of creation, the forging of elements, the birth of stars and galaxies, all from the familiar ingredients of matter and energy. Yet, as our cosmic understanding deepens, we find that the visible universe, the one we can observe with our telescopes and detect with our instruments, is but a small fraction of the whole. There are unseen forces and substances at play, weaving through the fabric of reality, shaping galaxies and dictating the universe's ultimate fate. These are the whispers of dark matter and dark energy. Imagine, for a moment, a magnificent cosmic ballet. You see brilliant dancers, the stars and galaxies, swirling and pirouetting across the vast stage of space. Their movements are graceful, powerful, seemingly dictating the rhythm of the entire performance. But as you watch more closely, as you apply the intricate laws of physics, you notice something perplexing. The dancers are moving much faster than they should, much faster than the visible forces around them could possibly explain. It's as if there's an invisible hand, a hidden conductor, guiding their motions with an unseen force. This unseen conductor, this silent orchestrator of the cosmic ballet, is what we call dark matter. The concept of dark matter arose from a series of observational puzzles that couldn't be explained by the visible matter in the universe. One of the first hints came in the 1930s when astronomer Fritz Zwicky was studying the Coma cluster of galaxies. He observed that the galaxies within the cluster were moving so fast that they should have flown apart, unable to remain gravitationally bound to each other. Based on the amount of visible matter present, it was as if a carousel was spinning so quickly that its riders should have been flung off. Yet they remained firmly in place. Zwicky proposed that there must be some unseen, non-luminous matter providing the additional gravitational pull, holding the cluster together. He called this missing mass dark matter. Decades later, in the 1970s, pioneering astronomer Vera Rubin and her colleagues provided compelling evidence for dark matter by studying the rotation curves of spiral galaxies. They observed that stars at the outer edges of galaxies were orbiting the galactic center at roughly the same speed as stars closer to the center. Rather than slowing down as expected, imagine a merry-go-round where the horses on the outside are moving just as fast as those in the middle. If all the mass were concentrated in the center, as the visible light suggested, then the outer stars should have been moving much slower, or they would simply fly off into space. This suggested that a significant amount of invisible mass must be distributed throughout the galaxy, extending far beyond the visible spiral arms, providing the necessary gravitational glue to keep the outer stars in their orbits. Since then, numerous other lines of evidence have consistently pointed to the existence of dark matter. Gravitational lensing, where the immense gravity of massive objects bends the light from background galaxies, reveals that there is far more mass in galaxy clusters than can be accounted for by their visible stars and gas. The distribution of matter in the cosmic microwave background radiation also aligns perfectly with models that include dark matter, even the large-scale structure of the universe. The cosmic web of galaxies and voids is best explained by dark matter providing the scaffolding upon which visible matter collects. So, what exactly is this mysterious dark matter? The truth is, we don't precisely know. It is dark not because it absorbs light, but because it doesn't interact with light or any other form of electromagnetic radiation. It doesn't emit, reflect, or absorb light, making it utterly invisible to our telescopes. It also doesn't interact with the strong or weak nuclear forces, meaning it doesn't form atoms or engage in the nuclear reactions that power stars. Its only known interaction is through gravity. The prevailing hypothesis is that dark matter consists of exotic, as yet undiscovered particles that interact very weakly with ordinary matter. These hypothetical particles are sometimes referred to as WIMPs, weakly interacting massive particles. Billions of WIMPs, if they exist, could be streaming through your body right now, completely unnoticed, like ghosts passing through walls. Scientists are actively conducting experiments deep underground, shielded from cosmic rays, hoping to detect these elusive particles as they occasionally, faintly, bump into atomic nuclei. Other theories propose alternative candidates, such as axions or sterile neutrinos, each offering a different glimpse into the nature of this unseen cosmic component. The search for dark matter particles is one of the most exciting and challenging frontiers in modern physics, a quiet quest for the invisible. The sheer abundance of dark matter is astonishing. Current cosmological models suggest that dark matter makes up about 27% of the total mass and energy of the universe. In contrast, all the ordinary matter, everything we can see and touch, all the stars, planets, galaxies, and gas only accounts for about 5%. This means that for every piece of visible matter, there's approximately 5 times as much dark matter silently influencing the cosmos. It's a humbling thought, isn't it, that the universe we perceive with our senses, the familiar one, is just a thin veil over a much vaster unseen reality. But the cosmic mysteries don't end there. As astronomers continue to refine their measurements of the universe's expansion, they encountered an even more perplexing enigma, one that completely overturned our previous understanding of the cosmos's ultimate fate, dark energy. For most of the 20th century, cosmologists generally believed that the universe's expansion, initiated by the Big Bang, would eventually slow down due to the collective gravitational pull of all the matter within it. The big question was whether it would slow down enough to eventually reverse and collapse in a big crunch, or simply continue to expand forever, gradually fading into a cold, dark big freeze. The ultimate destiny of the cosmos hinged on the balance between expansion and gravity. Then, in the late 1990s, 2 independent teams of astronomers, studying distant supernovae exploding stars as standard candles to measure cosmic distances and expansion rates, made a truly shocking discovery. They found that the universe's expansion was not slowing down as expected. Instead, it was accelerating. It was as if someone had pressed the cosmic accelerator pedal, making the expansion speed up over time. Imagine throwing a ball into the air, expecting it to slow down and eventually fall, only to watch it inexplicably speed up as it rises higher and higher. This discovery was so profound, so unexpected, that it earned the lead researchers the Nobel Prize in Physics in 2011. This acceleration implied the existence of a mysterious, pervasive force counteracting gravity, pushing space apart. This force, responsible for the universe's accelerating expansion, was dubbed dark energy. Unlike dark matter, which clumps around galaxies and clusters, dark energy appears to be smoothly distributed throughout space, acting like an intrinsic property of space itself. It's a form of energy inherent to the vacuum, generating a repulsive force that drives galaxies further and further apart. What is dark energy? This is perhaps the biggest open question in all of physics and cosmology today. The simplest explanation, proposed by Einstein himself over a century ago, is the cosmological constant. Initially, Einstein introduced this term into his equations of general relativity to ensure a static universe. A universe that neither expanded nor contracted, when Edwin Hubble later discovered that the universe was indeed expanding. Einstein famously called the cosmological constant his biggest blunder. But with the discovery of accelerating expansion, the cosmological constant has made a spectacular comeback. now representing the energy density of empty space itself. However, theoretical calculations based on quantum field theory predict a cosmological constant that is many orders of magnitude larger than what is observed. This vast discrepancy, often called the cosmological constant problem, is one of the most significant unsolved puzzles in modern physics. It suggests that our understanding of the vacuum, and perhaps of gravity at a quantum level, is still profoundly incomplete. Alternative theories for dark energy include the concept of quintessence, a dynamic, evolving field that permeates space, its energy density changing over time. Or perhaps, the acceleration is a sign that Einstein's theory of gravity needs to be modified on the largest cosmic scales. For now, dark energy remains largely an enigma, a profound mystery at the heart of our universe. The proportions of dark energy are even more staggering than dark matter. Current measurements indicate that dark energy makes up about 68% of the total mass and energy of the universe. This means that ordinary matter, the stuff of stars, planets, and us, is a mere 5% of the cosmos, while dark matter is about 27%, and dark energy dominates the rest. We are living in a universe largely composed of unknown, unseen entities. It's a humbling realization, suggesting that our observable reality is but a small island in an immense ocean of the unknown. The implications of dark energy are profound for the universe's ultimate fate. If the acceleration continues, the universe will expand faster and faster, causing galaxies to recede from each other at ever-increasing speeds. Distant galaxies will eventually move beyond our cosmic horizon, their light unable to reach us, rendering them forever invisible. The universe will become an increasingly lonely, cold, and empty place, eventually dominated by an expanding void, leading to the Big Freeze scenario. This long, slow fade into cosmic emptiness, driven by the relentless push of dark energy, is the current prevailing prediction for our universe's ultimate destiny. So, as you rest in this quiet space, let your mind ponder these immense, unseen components of our cosmos. Dark matter, the invisible scaffolding that holds galaxies together, and dark energy, the mysterious force accelerating the universe's expansion. Remind us of the vastness of what we still don't know. They are powerful whispers from the edges of our understanding, inviting us to remain curious, to embrace the profound mystery, and to find comfort in the fact that even in the greatest unknowns, there is a quiet, compelling beauty. The universe is full of secrets, and perhaps, in the stillness, you can feel the subtle influence of these unseen components, guiding you gently into a deeper state of peace. As our minds gently drift through the vastness of cosmic concepts, from the fiery birth of the universe to the enigmatic embrace of dark matter and dark energy, let us now turn our quiet contemplation to the very notion of nothingness, it seems. At first glance, a simple concept. Doesn't it an absence? A void? The complete lack of anything? Yet in the realm of physics and cosmology, nothing is far from simple. In fact, it's one of the most profound and perplexing ideas. A concept that stretches the very limits of our understanding and reveals the universe to be a place far stranger and more dynamic than we might ever imagine. Imagine, if you will, the deepest vacuum you can conceive, not the empty space between stars, which is actually teeming with faint radiation, cosmic dust, and the occasional wandering particle, but a space completely devoid of all matter, all energy, all fields, even space-time itself. This might be our intuitive idea of nothingness. However, according to the mind-bending principles of quantum mechanics, true nothingness, in this absolute sense, simply doesn't exist at the quantum level. The very fabric of existence is inherently jittery, uncertain, and alive with potential. This is governed by the Heisenberg uncertainty principle, which whispers that we can never precisely know both the position and momentum of a particle simultaneously. when applied to the vacuum of space. This principle implies that even in what appears to be utterly empty space, there are ceaseless, spontaneous fluctuations of energy. These are known as quantum fluctuations or zero-point energy. Imagine the vacuum not as a still, serene pond, but as a turbulent, boiling sea, constantly frothing with activity. For fleeting moments, particles and their corresponding antiparticles like an electron and a positron can spontaneously pop into existence from pure energy, only to annihilate each other almost immediately and vanish back into the vacuum. These are often called virtual particles because they exist for such an infinitesimally short time that they cannot be directly observed. But their effects are measurable, the famous Casimir effect, for example, where two uncharged. Parallel metal plates placed very close together experience a slight attractive force. Is a direct result of these quantum fluctuations in the vacuum. It's as if the virtual particles outside the plates exert more pressure than those between them. Pushing the plates together, this means that the vacuum of space, even in its emptiest state, is never truly empty. It is a vibrant, bubbling cauldron of potential, a constant dance of creation and annihilation, a silent testament to the universe's inherent dynamism. The nothing of physics is, in fact, a rich and complex something. It is full of latent energy, a quantum foam ready to burst forth with fleeting existence. This profound understanding of the vacuum has deep implications for our understanding of the universe's origin. If nothing is always something due to quantum fluctuations, then perhaps the universe itself could have emerged from one such fluctuation, a spontaneous burst of energy from the primordial vacuum. This idea, known as the universe from nothing hypothesis, suggests that the vast cosmos we inhabit might have originated from a tiny, quantum fluctuation in a pre-existing vacuum. Without needing an external cause or an initial something from which to spring, it's a concept that challenges our intuitive notions of creation, where something always comes from something else. But in the quantum realm, the rules are different. Here, the potential for creation is inherent in the very fabric of existence, even in its most seemingly empty state. The universe, in this view, is a grand, self-generating phenomenon, an ultimate expression of quantum probability. However, this doesn't fully explain the origin of space-time itself. The universe from nothing hypothesis often assumes a pre-existing vacuum, a space-like backdrop in which these quantum fluctuations occur. But what about the origin of space and time? This brings us back to the most profound questions about the Big Bang. If space-time began at the Big Bang, then what was before that if there was no space-time? Could there truly be any nothing in the sense of a stage for quantum fluctuations? This is where concepts like Stephen Hawking's no-boundary proposal come into play. As we explored earlier, Hawking suggested that if we consider space-time as a continuous, curved surface, then tracing it back to the beginning leads to a smoothly rounded South Pole, where time and space cease to have a distinct beginning in the conventional sense. There's no sharp edge, no singular point of creation from absolute nothingness, but rather a gradual rounding off, a transition from a state where our familiar notions of time and space are meaningless. In this view, the universe simply is. Without a before or a cause in the traditional sense, it's a universe that is self-contained and self-sufficient, a complete and elegant whole. The question of nothing also leads us to contemplate the ultimate fate of the universe. If, as current observations suggest, dark energy continues to drive the accelerating expansion of the cosmos, pushing galaxies further and further apart, then the universe will eventually become an incredibly vast, cold, and empty place. Distant galaxies will recede beyond our cosmic horizon, their light unable to reach us, rendering them forever invisible. Stars will eventually burn out. Black holes will evaporate over incomprehensibly long timescales, and even protons might eventually decay. In this scenario, known as the Big Freeze or the heat death of the universe, the cosmos will approach a state of ultimate thermodynamic equilibrium. There will be no more energy gradients, no more processes to drive change or complexity. The universe will be a cold, diffuse, and incredibly empty void, filled only with the lingering echoes of photons and perhaps a few widely scattered fundamental particles. This state of ultimate emptiness, this vast nothingness of activity and structure, is a sobering contemplation. It suggests a universe that, after billions upon billions of years of vibrant activity, finally settles into a state of profound stillness, a return to a cosmic quietude, albeit one fundamentally different from its earliest moments. But even in this ultimate emptiness, would it be truly nothing if quantum fluctuations persist? Then, even in the most dispersed, coldest future, the vacuum would still be a bubbling sea of virtual particles, constantly appearing and disappearing. Perhaps, even then, the potential for new creation, for new universes to spontaneously burst forth, would still exist, a testament to the universe's ceaseless, inherent dynamism. The concept of nothingness, therefore, is not a simple void, but a rich philosophical and scientific frontier. It challenges our intuitions, stretches our minds, and invites us to reconsider the very nature of existence. It reminds us that our familiar reality is built upon layers of profound mystery, and that even in the absence of tangible things, there is a fundamental activity, a boundless potential. As you allow these thoughts to gently settle in your mind, let yourself drift into the quiet contemplation of nothing. Perhaps it is a place of absolute peace, a blank canvas awaiting new creation, or perhaps it is a state of fundamental potential, forever bubbling with the possibility of new worlds. There is a profound comfort in embracing the unknown, in recognizing that even the most empty spaces are imbued with a quiet, powerful energy. Allow this sense of boundless possibility to wash over you, soothing your mind and guiding you deeper into a state of profound relaxation. The universe, in its very essence, is a testament to the extraordinary nature of apparent nothingness, an invitation to find stillness and wonder in the deepest of mysteries. As our quiet journey through the universe continues, gently touching upon its fiery birth, the elusive nature of time, and the profound mystery of nothingness. Let us now turn our minds to a concept that seems, at first glance, utterly contradictory to the vastness of space closeness. How can closeness exist in a cosmos so overwhelmingly immense, so filled with emptiness yet? It is precisely in this paradox that we uncover some of the most beautiful and deeply connected aspects of our existence. Consider, for a moment, the vast, cold expanse between celestial bodies. The distance between Earth and its nearest stellar neighbor, Proxima Centauri, is about 4.2 light-years. To put that in perspective, if you could travel at the speed of light, it would still take you over 4 years to reach it. And that's just the nearest star. The distances between galaxies are truly staggering, measured in millions or even billions of light-years in this grand cosmic tapestry. Everything seems incredibly far apart, isolated islands in an ocean of void. Yet, this perception of immense distance can be misleading. In a profound, almost poetic sense, everything in the universe is, in fact, intimately connected. This connection stems from the very beginning of the cosmos, from that singular, incredibly dense, and hot point we call the Big Bang. Imagine all the matter and energy of our observable universe compressed into an unimaginably tiny space, smaller than a single atom. At the moment of the Big Bang, in that primordial instant, every particle, every fundamental force, every nascent thought of existence was in intimate contact with every other. There was no far apart, only a unified, dense singularity. All that we see around us today, the sun, the distant galaxies, The very atoms in your body were once part of that same singular point. We are, quite literally, made of the same ancient stardust, forged in the same cosmic crucible. This shared origin is the deepest form of closeness, a fundamental unity that underlies all apparent separation, even as the universe expanded, stretching out space and carrying galaxies apart. The echoes of this initial closeness persisted. The cosmic microwave background, CMB radiation, that faint afterglow of the Big Bang, serves as a powerful reminder of this connection. When we observe the CMB, we are seeing the universe as it was 380,000 years after its birth, a time when it was still a relatively small, hot, and dense plasma. The remarkable uniformity of the CMB temperature across the entire sky, even in regions that are now billions of light years apart, testifies to the fact that these regions were once close enough to exchange heat and information, reaching a state of thermal equilibrium. Inflation, as we discussed, took this small, uniform region and stretched it out, preserving its initial homogeneity across vast distances. So even across the widest cosmic vistas, we are subtly connected by this shared thermal history, a ghostly warmth from a time when everything was truly close. Furthermore, the forces of nature themselves bind everything together in a profound web of interaction. Gravity, though the weakest on a personal scale, operates across infinite distances. However feebly, every atom in your body exerts a tiny gravitational pull on every star in the most distant galaxy. And in turn, every distant galaxy exerts a pull on you. This invisible, omnipresent force weaves a continuous thread of connection throughout the entire cosmos. It's a silent, constant embrace, pulling everything towards everything else, creating a subtle, undeniable closeness. The electromagnetic force, responsible for light and chemistry, binds atoms together, forms molecules, and enables the intricate dance of life. The light from a distant star travels across vast stretches of emptiness, only to be captured by your eye, allowing you to witness its ancient brilliance. This exchange of photons, these tiny messengers of light, bridges immense cosmic gulfs, bringing the distant close to us. The very existence of matter, of stable atoms and complex structures, is a testament to the powerful, binding nature of this force, creating closeness even at the subatomic level. And then there are these subatomic particles themselves, the fundamental constituents of matter. Particles in the quantum realm exhibit a perplexing phenomenon known as quantum entanglement. When two particles become entangled, they become intrinsically linked, regardless of the distance separating them. If you measure the property of one entangled particle, you instantly know the corresponding property of the other. Even if they are light years apart, it's as if they share an invisible, instantaneous communication channel, defying our classical understanding of space and time, while the implications of entanglement for macroscopic objects are still being explored. It suggests a profound, underlying interconnectedness at the very fabric of reality, a closeness that transcends distance, even in the deepest void, in what appears to be empty space. There is a subtle, pervasive presence, the vacuum energy or dark energy, this mysterious force, which drives the accelerating expansion of the universe, is not localized to galaxies or clusters. It is inherent to space itself, a property of the vacuum. This means that every cubic meter of empty space, no matter where it is in the cosmos, possesses a certain amount of this dark energy. It's an invisible field, a silent hum that permeates everything, creating a continuous medium, binding all regions of space in a unified, albeit expanding, fabric. In this sense, there is no true emptiness, no absolute void, only a field of latent energy that ensures a continuous, subtle closeness, perhaps the most profound form of closeness. However, is our own connection to the universe. We are not mere observers of the cosmos. We are an integral part of it. The atoms that make up our bodies, the carbon in our bones, the oxygen we breathe, the iron in our blood were forged in the hearts of stars that lived and died billions of years ago. We are, quite literally, stardust brought to life, sentient beings capable of contemplating the very universe from which we arose. Our existence is a direct consequence of the universe's long, majestic unfolding, a beautiful testament to the interconnectedness of all things. This realization can bring a profound sense of belonging, a quiet comfort in the midst of the vastness. We are not separate from the cosmos. We are intrinsically woven into its fabric. The same fundamental forces that shaped galaxies also orchestrate the delicate dance within ourselves. The same ancient starlight that brightens the night sky illuminates our understanding of cosmic origins. There is a deep, quiet peace in this shared ancestry, this undeniable bond with everything that exists. So, as you rest, let the idea of closeness gently settle in your mind. Despite the seemingly infinite distances, the universe is a symphony of interconnectedness, from the Big Bang's initial embrace to the subtle pull of gravity, from the invisible dance of quantum entanglement to the very particles that form your being. Everything is woven together in a grand, unified tapestry. There is no true isolation, only the illusion of separation. In this profound understanding of closeness, find your own quiet peace, a deep sense of belonging within the boundless, mysterious cosmos. Let this feeling of connection guide you into a restful and tranquil state. As our gentle journey through the cosmic tapestry approaches its quiet conclusion, we arrive at the profound and deeply personal contemplation of you. From the unimaginable fiery birth of the universe, through its vast and perplexing evolution, to the intricate dance of forces and particles, every step of this cosmic story has led, in some mysterious way, to this very moment, to your very existence. You are not merely an observer of the cosmos. You are an intrinsic, irreplaceable part of its grand narrative. Imagine, for a moment, the sheer improbability of your being. From the chaotic quantum fluctuations of the Planck era to the smoothing expanse of inflation. From the delicate balance of matter over antimatter to the forging of the first light elements. And then the eons of cosmic darkness leading to the birth of stars and galaxies. Each step was a cosmic prerequisite for your eventual appearance. The carbon in your cells, the oxygen you breathe, the iron in your blood. These fundamental building blocks were not present at the Big Bang. They were forged in the fiery hearts of ancient stars, in cataclysmic supernovae explosions that scattered their precious contents across the nascent cosmos. You are, quite literally, made of stardust, the recycled remnants of cosmic giants that lived and died billions of years ago. This profound connection means that your body is a microcosm of the universe itself. The forces that bind atoms in a distant galaxy are the same forces that hold your very cells together. The grand dance of gravity that sculpts cosmic structures also keeps your feet on the ground. The light from a distant star, traveling across billions of light years, ends its journey in the sensitive detectors of your eyes, allowing you to witness its ancient brilliance. You are an intricate, living bridge between the distant and the immediate, the vast and the minuscule. Consider the incredible complexity that has arisen from simple beginnings. From a universe initially composed of just hydrogen and helium, the cosmic alchemy of stars created all the heavier elements. These elements then combined in increasingly intricate ways, forming molecules, then complex organic compounds, eventually leading to the astounding phenomenon of life. And within that vast, diverse tapestry of life, consciousness emerged the ability to observe, to question, to wonder, and to contemplate the very universe from which it arose. You possess this unique capacity. You are the universe contemplating itself through your senses, your thoughts, your very consciousness. The cosmos gains an awareness of its own existence, its own history, its own beauty. The light from a distant supernova that reaches your eye is not just a scientific datum, it's a moment of cosmic revelation, filtered through the lens of your unique perception. The understanding you gain, the awe you feel, the questions you ponder. These are the universe's own inquiries into its nature. This brings us to a beautiful, humbling truth. The universe needs you as much as you need the universe. It needs you to witness its grandeur, to decode its secrets, to tell its story, without conscious observers, without minds capable of asking why and how. The universe's incredible journey would unfold in silent, unperceived majesty. You are the lens through which the cosmos gains meaning, a living testament to its capacity for self-awareness. In a sense, your journey through life, with its moments of joy and sorrow, challenge and triumph, is a continuation of the universe's grand evolution. Every decision you make, every act of kindness, every creative endeavor, adds another layer to the unfolding cosmic story. You are a unique expression of the universe's boundless potential, a tiny yet infinitely precious ripple in the vast ocean of existence. As you reflect on this profound connection, let it bring you a deep sense of peace and belonging in moments of uncertainty or solitude. Remember that you are woven into the very fabric of the cosmos. You are not separate from the stars, the galaxies, or the fundamental forces that govern all things. You carry the stardust within you, the echoes of the Big Bang in your very atoms. This awareness can be a source of immense comfort. There is a quiet strength in recognizing your place within this grand, cosmic narrative. All the wonders we have explored from the Planck era to dark energy, from the dance of time to the paradox of closeness, are not just abstract concepts. They are the very threads that weave your existence. You are a living miracle, a conscious manifestation of the universe's journey through time. As this quiet contemplation draws to a close, allow these profound truths to settle gently within your mind. Feel the ancient connection to the stars, the quiet hum of cosmic forces within and around you. There is no need for striving, no need for grasping. Simply be present in this moment, fully aware of your unique and precious place in the universe. Let this feeling of boundless connection guide you into a state of profound relaxation, a deep and peaceful stillness. Thank you for joining me on this gentle journey through the cosmos. May the peace and wonder of the universe accompany you always.